What if everything you thought you knew about the universe was built on a foundation that isn't solid at all, but is instead a seething, turbulent ocean of pure possibility? Picture the vast emptiness of space, not as a silent, dark void between stars and galaxies, but as a stormy, churning sea where reality itself is constantly boiling, flickering in and out of existence on the smallest scales imaginable. This isn't science fiction, this is the mind-bending frontier of modern physics, a concept known as quantum foam. It's the idea that at the very tiniest levels at the Planck scale, the fabric of space-time isn't smooth and continuous. It's a chaotic, foamy mess full of tiny, fleeting wormholes, virtual particles, and fluctuations that challenge everything we thought we understood from Einstein's theory of relativity. Our classical view of a predictable, clockwork universe completely shatters here, replaced by a realm of inherent uncertainty and wild, energetic froth. This quantum foam represents one of the greatest unsolved mysteries in all of science, a place where our two most successful theories, general relativity and quantum mechanics, meet and completely break down, refusing to play by the same rules. It's a hidden layer of reality, operating at a scale so infinitesimally small that we can't directly observe it, yet its potential implications are cosmic in scope. It could hold the keys to understanding the birth of the universe, the nature of black holes, and even the possibility of other dimensions lurking just beyond our perception. The very ground beneath our feet, the space through which light travels, is potentially this vibrant, dynamic substance, and that realization changes everything. It forces us to confront a universe that is far stranger, far more alive, and infinitely more mysterious than we ever dared to dream. That sense of profound wonder and mystery is exactly what we're going to explore together in this video. We're about to dive deep into 30 of the most incredible, provocative, and awe-inspiring theories that scientists have proposed to explain this chaotic foundation of reality. From the idea that our universe is a hologram projected from its boundaries, to theories suggesting that this foam allows for microscopic time travel, we will journey through concepts that stretch the imagination to its absolute limits. This is an invitation to join a voyage to the very edge of human knowledge, to peer into the foam and see what secrets might be bubbling up. So, get comfortable, open your mind, and let's begin our exploration of 30 theories about the universe's quantum foam. Our first stop on this journey into the quantum foam takes us to a theory that reimagines the very canvas of the cosmos. This is the idea of the space-time lattice. For centuries, from Newton to Einstein, we've treated space and time as a smooth, continuous fabric, a stage upon which the drama of the universe unfolds. But what if that stage isn't seamless? What if, when you zoom in far enough, you discover that reality has a fundamental resolution, much like a digital photograph? The theory of the space-time lattice proposes exactly that. It suggests that at the tiniest possible scale, the Planck length, the universe is not continuous but granular. It's composed of unimaginably small, discrete units of space and time, creating a fixed, grid-like structure that underpins everything. Think of it like the pixels on your screen. From a distance, the image appears smooth, but up close, you can see the individual blocks that construct the whole picture. In this view, the universe is fundamentally pixelated. This notion of a pixelated reality directly challenges the core of Einstein's general relativity, which relies on a perfectly smooth, deformable space-time continuum. In a lattice universe, there is a limit to how small things can get and how precisely we can measure. You can't have half a pixel of space or a fraction of a pixel of time. They are the smallest possible units. This has profound implications. For one, it could provide a natural explanation for the universe's ultimate speed limit, the speed of light. In a smooth continuum, there's no obvious reason why something couldn't go faster than light. But in a pixelated lattice, the speed of light might simply be the maximum processing speed of the cosmos, the rate at which information can hop from one discrete cell of the lattice to its immediate neighbor. It would be the cosmic speed limit hard-coded into the architecture of reality itself. The implications ripple out even further, touching upon the very nature of matter and motion. In this framework, a particle moving through space isn't gliding on a smooth sheet. It's effectively jumping from one lattice point to the next. This could potentially resolve some of the thorniest infinities that plague theoretical physics, particularly those that arise when dealing with the extreme gravity of black holes or the moment of the Big Bang. The lattice provides a natural cutoff, a finest level of detail that prevents calculations from blowing up into meaningless infinities. It's a theory that offers a tantalizing blend of the familiar and the revolutionary, suggesting that the universe operates with a built-in precision, a fundamental graininess that has been hiding in plain sight all along. Now let's turn up the magnification even further and peer into the very substance of this foam. If the space-time lattice gives us a structure, then this next theory fills that structure with a breathtaking, almost violent activity. Welcome to the world of virtual particle pairs. According to quantum field theory, what we call empty space is anything but empty. It is instead a seething, frenetic broth where particle-antiparticle pairs are constantly, spontaneously bubbling into existence. One moment there is nothing, the next an electron and its antimatter counterpart, a positron, flicker into being. They exist for an almost impossibly brief moment, borrowing energy from the universe under the rules of quantum uncertainty, before they inevitably collide and annihilate each other, returning the energy and vanishing back into the void. This isn't a rare event, it's happening everywhere all the time at an unimaginable rate. A better analogy than a still pond might be a colossal pot of water at a rolling boil, with bubbles of reality forming and popping in a relentless, chaotic dance. This ceaseless activity of creation and destruction, known as vacuum fluctuation, is a cornerstone of our modern understanding of physics. It's not just a mathematical curiosity, we have solid experimental evidence that it's real. One of the most striking demonstrations is the Casimir effect. Imagine placing two perfectly smooth, uncharged metal plates extremely close together in a vacuum. You might expect nothing to happen, but something remarkable occurs. The space between the plates is so narrow that only certain wavelengths of these virtual particles can pop into existence there. Outside the plates, however, all wavelengths can form. This difference in pressure, with more virtual particles pushing on the outside of the plates than on the inside, creates a measurable force that actually pulls the plates together. It's a direct physical consequence of the ghostly dance of particles in the quantum foam, a force born from the energy of nothingness itself. But the influence of these virtual particles extends far beyond a laboratory demonstration. They play a crucial role in the life cycles of stars and may even hold the key to the ultimate fate of the cosmos. For instance, near the event horizon of a black hole, the intense gravity can tear a virtual particle pair apart. One particle falls into the abyss while the other escapes, stealing a tiny amount of the black hole's energy in the process. This is Hawking radiation, a theoretical mechanism by which black holes slowly, over eons, evaporate. On an even grander scale, this same quantum vacuum energy is thought by many cosmologists to be the driving force behind the accelerated expansion of the universe, a phenomenon we call dark energy. So, from the force between two tiny plates to the evolution of the entire cosmos, the fleeting existence of virtual particles in the quantum foam leaves an indelible mark on the universe we inhabit, proving that the most profound effects can emerge from the most ephemeral of causes. Building directly on the idea of a universe teeming with transient energy, we arrive at a theory that transforms this chaotic froth into a cosmic transportation network. This is the wormhole nexus. Imagine that the bubbling virtual particles and fluctuating space-time we just discussed aren't just random froth. Instead, envision the quantum foam as an impossibly dense, intricate web of tunnels, each one a minuscule, short-lived wormhole. In this view, every single point in space is connected to every other point by a vast, ever-changing labyrinth of these microscopic bridges, constantly forming, collapsing, and reforming in the blink of a Planck time. The empty void is not just active, it is profoundly interconnected, a nexus of potential shortcuts woven into the very fabric of reality. The theoretical basis for this comes from some of the most brilliant minds in physics. Decades ago, John Wheeler, who actually coined the term quantum foam, suggested that its turbulent structure might be dominated by these tiny wormholes. Later, Stephen Hawking and others explored how the wild, probabilistic nature of the quantum world could allow for such bizarre distortions of spacetime to pop in and out of existence. These aren't the stable, spaceship-sized wormholes of science fiction. They are quantum-scale imperfections, smaller than a subatomic particle, and they exist for a duration so brief it's almost meaningless. Yet, according to this theory, they are everywhere, trillions upon trillions of them in the space occupied by a single atom, forming the foundational texture of the cosmos. This leads to a profoundly exciting possibility. Could these fleeting, microscopic tunnels be the raw materials for building larger, stable, and potentially traversable wormholes? The idea is that under the right conditions, perhaps with an immense amount of energy or a sophisticated understanding of quantum gravity, these natural, microscopic structures could be coaxed into linking up or inflated to create a macroscopic bridge between two distant points in space or even time. It's a concept that shifts the challenge of wormhole engineering from creating a tunnel from scratch to finding a way to stabilize and expand a structure that the universe is already constantly building for us. Instead of forcing space-time to bend, we would be learning to nurture a connection that is already there, hidden within the foam. If such a thing were possible, the implications for concepts like faster-than-light travel would be staggering. A ship wouldn't need to break the universal speed limit by moving through normal space. It could, in theory, use a stabilized wormhole nexus as a shortcut, arriving at a destination light years away almost instantaneously by taking a detour through the quantum underworld of spacetime. This doesn't violate relativity because the ship itself isn't traveling faster than light through local space. It's simply taking a different, drastically shorter route, like folding the page of a book to bring two distant points together. The journey through the wormhole could be nearly instantaneous, making interstellar exploration a tangible prospect rather than a distant dream. Beyond mere travel, this nexus theory forces us to reconsider the fundamental nature of connectivity in our universe. It suggests that what we perceive as vast, empty distances separating galaxies might be an illusion, with everything being intrinsically linked at the quantum level. The separation between you and the most distant star could be an artifact of our macroscopic perception, while in the unseen, foamy depths of reality, a direct, if ephemeral, connection might always exist. This idea pushes the boundaries of physics and philosophy, hinting that the universe is far more interconnected and accessible than our everyday experience would ever suggest, with every point in spacetime just a quantum hop, skip, and a jump away from every other. From the interconnected labyrinth of microscopic wormholes, we venture into a theory that is perhaps even more radical, one that challenges our most basic assumptions about dimensions and reality itself. This is the holographic principle, an idea so profound that it suggests everything we see and feel in our three-dimensional universe, including the very quantum foam we've been exploring, might be nothing more than an incredibly detailed illusion, a holographic projection originating from a two-dimensional surface at the edge of the cosmos. To grasp this, picture a common hologram on a credit card. That shimmering, three-dimensional image you see doesn't have any real depth. all of its information is encoded on the flat, two-dimensional surface of the sticker. The holographic principle applies this same logic to the entire universe, proposing that our reality, in all its rich complexity, is a vast cosmic hologram projected from a distant two-dimensional boundary. The origins of this startling idea are deeply rooted in the study of black holes and the fundamental laws of thermodynamics. In the 1970s, physicist Jacob Bekenstein made a groundbreaking discovery. He found that a black hole's entropy, which is a measure of its hidden information or disorder, is not proportional to its volume as you might expect, but to the surface area of its event horizon. This was a huge clue. It implied that all the information about whatever matter and energy fell into the black hole was not lost inside its infinite depth, but was somehow stored or encoded on its two-dimensional boundary. Later, Stephen Hawking confirmed that black holes do indeed radiate energy and slowly evaporate, raising a terrifying question. When a black hole vanishes, what happens to all that information? The holographic principle emerged as a powerful solution, suggesting the information is never truly inside the black hole to begin with. It was always on the surface, and the three-dimensional space within, with its stars, planets, and even the quantum foam, is just a projection of that data. This leads to an extraordinary implication for the nature of reality. If the information content of a volume of space is determined by its surface area, then there is a fundamental limit to how much information any region of the universe can contain. You cannot pack an infinite amount of data into a finite space. This provides a beautiful, natural explanation for the pixelated nature of the space-time lattice we discussed earlier. The universe isn't just granular, it's holographic. Each pixel on the two-dimensional boundary projects a bit of information that makes up our three-dimensional world, and the Planck area sets the ultimate size for these pixels. The frantic, churning activity of the quantum foam, with its virtual particles and microscopic wormholes, might not be the primary reality. Instead, it could be a secondary effect, a kind of visual static or artifact generated by the immense amount of information processing happening on the cosmic projector screen at the edge of everything. Think of it like a massively complex computer simulation, but one running on a two-dimensional surface. The physics we experience in three dimensions, from the force of gravity to the collision of atoms, would be an emergent property of quantum interactions and entanglement on that lower dimensional surface. This doesn't mean our reality is fake. It means that what we perceive as solid and three-dimensional is a direct consequence of processes unfolding in a universe with one less dimension. The foam, then, is the visible texture of this projection, the graininess that becomes apparent when we push our observations to the absolute limit. It's the proof that we are living inside a cosmic hologram where the true laws of physics are written in two dimensions, and we are all just incredibly vivid characters in a spectacular three-dimensional shadow play. If the holographic principle makes you question the very dimensions of reality, then our next theory will fundamentally change how you picture the substance of space itself. This is the world of loop quantum gravity and its central idea, spin networks. While many approaches to unifying gravity with quantum mechanics try to quantize gravity as a force, loop quantum gravity takes a dramatically different path. It proposes that space itself is not a background stage. It is the main actor, and it's made of something. In this theory, the quantum foam isn't just a chaotic froth, it's a breathtakingly intricate and dynamic fabric woven from individual, discrete threads of space. Imagine a cosmic tapestry, but instead of thread, the fundamental material is tiny, one-dimensional loops of gravitational field, vibrating and intertwining. These are the literal loops in loop quantum gravity. These loops don't exist in space, they are space. When they link together, they form a web-like structure known as a spin network. Picture a vast three-dimensional mesh of interconnected lines with tiny volumes trapped inside them. Each intersection point in this network, or node, represents a tiny, indivisible grain of space, a quantized volume at the Planck scale. The links connecting them represent the surfaces between these volumes. This is the true nature of the quantum foam in this theory, a granular, pixelated geometry that is woven from the bottom up. The frantic activity we've discussed isn't just particles bubbling in a void. It's this network itself evolving, vibrating, and changing its configuration over time. Space is not smooth and continuous. It is this polymer-like structure, and the familiar, continuous space of our daily lives emerges only when we zoom out, much like a smooth piece of fabric emerges from the interwoven threads of cotton. This discrete structure provides a powerful solution to one of the most vexing problems in all of physics, the singularity. In Einstein's general relativity, singularities are points of infinite density and curvature, like the very center of a black hole or the moment of the Big Bang, where the laws of physics as we know them simply break down. But in a spin network, such infinities are impossible by design. Because space is quantized, you cannot compress a volume of matter or energy down to an infinitely small point. There is a smallest possible volume, a fundamental pixel of reality. When matter is crushed under immense gravity, it reaches a point where it simply cannot be compressed any further. This means that at the heart of a black hole, instead of a mathematical singularity of infinite density, there may be a region of unimaginably high but finite density, a quantum bounce where the fabric of spacetime, pushed to its absolute limit, responds with a force that prevents its own destruction. The evolution of this cosmic tapestry is where the theory gets its full name, loop quantum gravity. A spin network is a snapshot of space at a single moment in time. But when we introduce time into the picture, the network begins to pulse and change. The nodes and links do not sit still. They vibrate and reconfigure, creating a four-dimensional history known as a spin foam. This spin foam is the dynamic version of the quantum foam. It's not just a static structure, but a record of how space itself evolves. Visualize the spin network not as a fixed sculpture, but as a living, breathing entity where the connections between grains of space are constantly updating, creating a rich, foam-like geometry across spacetime. This evolving foam provides a completely background-independent theory of quantum gravity. The dynamics of the universe are determined purely by the relationships between these discrete elements, with no need for a pre-existing stage for them to play out on. This perspective offers a startlingly new vision of the Big Bang. Instead of a mysterious explosion from a point of infinite density, loop quantum gravity suggests our universe could have been born from a great bounce. A previous cosmos, perhaps similar to our own, may have contracted under its own gravity. But instead of collapsing into a singularity, the intense compression reached a point where the repulsive force generated by the quantized geometry became dominant, causing the universe to rebound and expand into the one we inhabit today. There was no nothing before the bang. There was a before, a different phase of the universe's evolution, with the Big Bang marking a profound transition rather than an absolute beginning. This paints a picture of a cyclical or rebounding cosmos, where the quantum foam itself possesses a resilience that prevents its own ultimate collapse, offering a glimpse into a potentially eternal and ever-transforming universe. Now, if the idea of space as a woven tapestry of loops intrigues you, wait until you see a theory that literally builds the universe from the ground up, one tiny geometric piece at a time. This is the fascinating world of causal dynamical triangulations. Think back to children's toys. Imagine a huge box filled with nothing but simple, identical triangular building blocks. Now imagine those blocks are the fundamental building blocks of spacetime itself. This theory does exactly that. It proposes that we can understand the entire architecture of the cosmos by gluing together vast numbers of these basic geometric shapes called simplices in a very specific way. It's a radically simple and beautifully computer-friendly approach to quantum gravity, one that lets us run a kind of digital experiment on the birth of the universe. The key to this entire approach lies in the word causal. This isn't just a random pile of blocks. There are strict rules for how they can connect. In this model, each building block has a built-in directionality, an arrow of time. When you glue them together, you must always connect the past of one block to the future of another. This enforces a universal causality, meaning that cause must always precede effect at every single level of the simulation. Without this rule, the digital universe that emerges is a chaotic mess, a jumbled, crumpled froth with an infinite number of dimensions, a place where physics as we know it couldn't possibly exist. But when you impose this simple rule of cause and effect, something almost magical happens. From this sea of connected triangles, a smooth, large-scale universe begins to crystallize. As you add more and more of these tiny geometric pieces, following the causal gluing rules, the model undergoes a phase transition. The chaotic, foamy jumble at the smallest scales organizes itself, and a classical, four-dimensional spacetime emerges all on its own. It's like watching a crystal form from a turbulent liquid. Individual molecules are moving randomly, but as they bind together, a beautiful, orderly structure appears. In the same way, the simple, bottom-up rules of causal dynamical triangulations give rise to the familiar, smooth fabric of space and time that we experience, without anyone having to program that smoothness in from the start. The theory doesn't assume a four-dimensional world, it derives one from first principles. This emergence of four dimensions is a spectacular result. Out of all the possible ways space-time could configure itself, this simple model consistently generates a universe with three extended spatial dimensions and one dimension of time. The other potential dimensions are effectively curled up so tightly at the Planck scale that they are unobservable, leaving us with the four-dimensional stage upon which our lives play out. This provides a powerful counter-argument to the idea that our universe's dimensionality is just a random accident. It suggests that a stable, classical universe capable of supporting complex structures like galaxies, planets, and life might naturally favor a four-dimensional form when it emerges from the quantum foam. So, the very fact that we experience a world of three spatial dimensions and one time dimension could be a direct consequence of the universe's need for stable, causal structure at its most fundamental level. But to truly appreciate the radical implications of these bottom-up approaches to spacetime, we must confront what is perhaps their most unsettling consequence, the complete dissolution of time as we know it. This brings us to our seventh theory, the problem of time. In our everyday experience, time is an undeniable, universal river flowing smoothly and uniformly from the past through the present and into the future. It's the steady drumbeat of the cosmos, a backdrop against which all events unfold. Yet, when we descend into the chaotic depths of the quantum foam, this reliable river seems to evaporate into mist. In a world built from discrete, fluctuating grains, the very concept of a single, universal time may break down completely. Think of it like trying to use a precise stopwatch in the middle of a bubbling, chaotic foam. On the surface of a still pond, you can mark time perfectly. 1 second follows another in an orderly procession. But if you plunge that stopwatch into a turbulent, frothing liquid, its function becomes meaningless. Bubbles are constantly forming, merging, and popping all around it. The mechanism jitters and stalls. There is no consistent rhythm or flow to measure. This is the fate of time in the quantum foam. At the Planck scale, where spacetime itself is a dynamic, ever-changing froth of geometries, there is no smooth, continuous timeline. Each fluctuating grain, each microscopic wormhole, each vibrating loop in the spin network might have its own independent rate of change. There is no master clock for the universe ticking in the background. Instead, there is a multitude of local clocks, all ticking out of sync with one another. This isn't just a technical detail, it strikes at the very heart of physics. virtually all our fundamental equations, from Newton's laws to Einstein's relativity, treat time as a fundamental parameter. They describe how things change with time, but in a theory like loop quantum gravity, where space-time emerges from the relationships between discrete elements, time is not an input, it is an output. The theory is inherently timeless at its most fundamental level. The dynamics are described by the changing configurations of the spin network, and from that complex evolution, a notion of time can be derived, much like the smooth flow of a movie emerges from the rapid succession of individual static frames. In this view, time is not a river, but a consequence of correlation and change. Your perception of time flowing is a result of the countless microscopic changes happening in the quantum networks that make up your brain and the world around you. Now, if time itself becomes a fuzzy, local concept in the foam, what does that mean for the sequence of events and the principle of causality, the idea that a cause must always come before its effect? This is where the situation becomes truly mind-bending. In the smooth space-time of general relativity, causality is clearly defined by what we call light cones. An event can only influence other events that lie within its future light cone. But in the quantum foam, with its microscopic wormholes and wildly fluctuating geometries, these light cones could become porous. Information might find shortcuts, or the very sequence of events could become probabilistic. Imagine two events, event A, a light turning on, and event B, a person seeing the light. In our classical world, A always causes B, but in the foam, there is a tiny, non-zero probability that the fluctuations could create a configuration where the effect, the person seeing the light, precedes the cause, the light turning on. On average, over large scales, causality holds firm, which is why our macroscopic world appears so orderly. But at the ultra-small scale, the unwavering arrow of time might become a flickering, probabilistic suggestion. This doesn't mean you could go back and prevent your own birth. Such macroscopic paradoxes are still fantastically unlikely. But it does mean that at the foundation of reality, the rigid chain of cause and effect might be replaced by a looser, statistical correlation, revealing a universe that is fundamentally acausal at its very core. Yet this uncertainty hovering at the heart of time and causation isn't the only way the quantum foam reaches up to shape the cosmos on the grandest of scales. In fact, its persistent, seething energy might be the hidden engine behind the single most profound discovery in modern cosmology, the accelerating expansion of the universe. This brings us to our eighth theory, which posits that the quantum foam is dark energy. For decades, astronomers have known that the universe is not just expanding, but that this expansion is speeding up, as if some mysterious, repulsive force is stretching the very fabric of space itself. The source of this cosmic repulsion was dubbed dark energy, and it constitutes about 70% of the total energy content of the cosmos. Yet its true nature has remained one of the greatest enigmas in all of science. The quantum foam offers a tantalizingly direct explanation. Recall the unceasing dance of virtual particle pairs that define the foam, a vacuum brimming with transient energy. According to Einstein's theory of general relativity, energy, in all its forms, has a gravitational effect. Most forms of energy, like matter or radiation, create an attractive gravitational pull which slows the cosmic expansion. But the vacuum energy inherent in the quantum foam is different. The equations of general relativity contain a term known as the cosmological constant that represents a constant energy density permeating all of space. If this energy is positive, as it is for the quantum vacuum, it generates a negative pressure, a kind of gravitational repulsion. Think of it like this. While the mass of a planet pulls things inward, the relentless bubbling of the vacuum pushes space itself outward, acting as a sort of anti-gravity that drives galaxies apart at an ever-increasing rate. In this view, dark energy isn't a mysterious new substance. It is the gravitational signature of the quantum foam itself, the collective push of a universe built on a foundation of pure, energetic potential. Yet this elegant idea immediately confronts a colossal problem, one so severe it has been called the worst theoretical prediction in the history of physics. When physicists attempt to calculate the expected value of this vacuum energy by summing up all the contributions from every possible quantum fluctuation in the foam, the result is absurdly, catastrophically large. The calculation suggests an energy density that should be at least 120 orders of magnitude. That's a 1 with 120 zeros after it, greater than what we actually observe from the measured rate of cosmic expansion. A universe with that much vacuum energy would have been torn apart in the first instance after the Big Bang. Stars, planets, and life would have been utterly impossible. The fact that we exist to observe a relatively sedate acceleration means that our theoretical estimate is spectacularly wrong, a discrepancy that highlights a deep gap in our understanding of how gravity interacts with the quantum world. So, how do we resolve this staggering mismatch? Physicists have proposed several compelling, though speculative, solutions. One possibility involves a delicate, near-perfect cancellation. Perhaps different types of particles and fields in the universe contribute positive and negative amounts of vacuum energy that almost but not entirely cancel each other out. The tiny residual left over, an almost immeasurably small fraction of the total, could be the dark energy we observe. Another, even more profound idea is the concept of the anthropic principle, which suggests that the value of the cosmological constant isn't fixed by a fundamental law, but can vary across different regions of a vast multiverse. We simply find ourselves in one of the rare universes where the vacuum energy is small enough to allow for the formation of galaxies and the evolution of life. In most other universes, the value is too large or too negative, and no observers ever arise. Our existence, therefore, selects for the strangely small but non-zero value we measure. Ultimately, the quest to understand dark energy as a manifestation of the quantum foam forces us to confront the limits of our current theories. It strongly suggests that a successful theory of quantum gravity will not only describe the foam's structure, but will also provide a mechanism to naturally explain why its net energy is so infinitesimally small, yet crucially not zero. This isn't just a minor accounting error, it's a fundamental clue about how the universe balances itself on a knife's edge. The accelerating expansion of the cosmos, a phenomenon observed across billions of light years, may be the most visible and lasting testament to the frantic, invisible activity occurring in the quantum foam beneath our feet, linking the very large to the very small in a single, breathtaking narrative. But this intimate connection between the quantum foam and the cosmic expansion leads us directly to one of the most perplexing and embarrassing problems in all of modern physics, a numerical catastrophe that lies at the heart of our ninth theory. You see, if the vacuum energy of the quantum foam is indeed the source of the cosmological constant, then we should be able to calculate its strength. When physicists perform this calculation, they sum up the contributions from every conceivable quantum fluctuation in that seething vacuum. They account for every virtual particle pair, every field vibration, every possible energy mode down to the Planck scale. The result of this straightforward calculation is a number so monumentally huge it defies comprehension. The theoretical prediction for the vacuum energy density exceeds the actual, observed value of dark energy by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. This isn't just a small error, it is the single worst prediction in the entire history of science, a discrepancy so vast it suggests something is profoundly wrong with our understanding. To grasp the sheer scale of this error, imagine calculating the distance from Earth to the nearest star and being off by a distance smaller than the diameter of a single proton. That level of inaccuracy would still be trillions upon trillions of times more precise than our vacuum energy calculation. This colossal mismatch is known as the cosmological constant problem, and it represents a glaring red flag that our theories of the very large and the very small are fundamentally incompatible when they meet in the quantum foam. It tells us that either our method of calculating the vacuum energy is completely misguided, or there is some exquisite hidden mechanism in the universe that cancels out almost all of this energy, leaving behind only the faintest whisper we detect as dark energy. This isn't a minor puzzle, it's a crisis that keeps cosmologists and theoretical physicists awake at night. So how could such an enormous error occur? The problem stems from a fundamental clash of frameworks. In quantum field theory, the vacuum is teeming with energy, and we calculate that energy by summing up all the possible fluctuations. But in general relativity, all forms of energy, including this vacuum energy, curve spacetime and influence the expansion of the universe. The issue is that we are using a quantum mechanical calculation and plugging it directly into a classical gravity equation without a proper theory of quantum gravity to guide us. It's like trying to use the rules of a card game to govern the play of a board game. The pieces just don't fit together correctly. The quantum calculation gives an enormous number, while the cosmological observation demands an incredibly tiny one, and we have no established principle to reconcile them. Several compelling, though speculative, solutions have been proposed to escape this numerical nightmare. One prominent idea is that of a delicate cancellation or fine-tuning. Perhaps the universe contains different types of quantum fields, some contributing positive energy and others contributing negative energy to the vacuum. Through some unknown symmetry or mechanism, these vast positive and negative contributions could cancel each other out to an incredible degree of precision, leaving behind only the minuscule, non-zero residue that we observe as dark energy. This would be like adding a positive number with 120 digits to a negative number of almost identical magnitude, resulting in a net value of just a few digits. The challenge with this idea is explaining why the cancellation is so perfect. It seems to require an unbelievable coincidence. This leads to another, even more radical explanation, the anthropic principle. This line of reasoning suggests that the value of the cosmological constant isn't determined by a unique fundamental law. Instead, in a vast multiverse, a cosmos comprising an infinite number of separate universes, the value of the vacuum energy could be different in each one. In the overwhelming majority of these universes, the cosmological constant is enormous. In those worlds, the repulsive force of dark energy is so powerful that spacetime expands so rapidly that no galaxies, stars, or planets can ever form. It's a sterile, empty cosmos. We, of course, find ourselves in one of the exceptionally rare universes where the cosmological constant is just small enough to allow for the slow gravitation. This relentless, seething activity of the quantum foam doesn't just shape the cosmos on the grandest scales. It also dictates the ultimate fate of its most mysterious and terrifying object. Our 10th theory takes us to the precipice of a black hole, a place of unimaginable gravity, and reveals how the foam is slowly, patiently dismantling it. This is the story of black hole evaporation, a revolutionary idea first proposed by Stephen Hawking that forever linked the fate of these cosmic monsters to the ephemeral whims of the quantum world. It all begins with that same process we've explored, the spontaneous creation of virtual particle-antiparticle pairs in the vacuum. But near the event horizon of a black hole, this everyday quantum occurrence takes on a profound destructive power. Imagine the empty space just outside the point of no return, a region dominated by the black hole's immense gravitational field. Here, the quantum foam is constantly bubbling, and a virtual particle pair flickers into existence. Under normal circumstances, these two partners would annihilate each other almost instantly, returning their borrowed energy to the vacuum. However, in the extreme gravity near the event horizon, a cosmic robbery can occur. The tidal forces are so powerful that they can rip the two particles apart before they have a chance to recombine. In this scenario, one particle falls across the event horizon, vanishing forever into the black hole's interior, while its partner escapes into space, carrying away energy. The incredible twist is that for energy to be conserved, the particle that falls in must have negative energy relative to the outside universe. From the perspective of a distant observer, the black hole has just effectively emitted a particle, a phenomenon we now call Hawking radiation. This process, repeated across the entire surface of the event horizon, transforms the black hole from an eternal trap into a slowly evaporating object. The escaping particle carries away a tiny bit of the black hole's mass energy. It's a minuscule loss for a colossal object, but it is constant, over time, across spans of time that are almost incomprehensible. For a stellar mass black hole, we're talking timescales far longer than the current age of the universe. This steady trickle of radiation causes the black hole to lose mass. And as it loses mass, its event horizon shrinks, which in turn increases the temperature of the Hawking radiation it emits. This creates a feedback loop. The evaporation process accelerates as the black hole gets smaller and hotter. The final stage of this evaporation is a crescendo. A very small, very hot black hole would emit radiation at a ferocious rate, culminating in a final, explosive burst of energy as it vanishes completely from existence. This theory provides a stunning resolution to what seemed like a fundamental paradox. Before Hawking's work, black holes were thought to be truly black, objects that could only grow, eternally consuming matter and energy while giving nothing back. They violated a cherished principle in physics: that information cannot be destroyed. Hawking radiation showed that black holes are not permanent fixtures of the cosmos. They have a life cycle. They are born from the collapse of massive stars. They live by consuming, and they ultimately die by evaporating, returning their energy, albeit in a scrambled thermal form, back to the universe. The quantum foam, therefore, acts as a cosmic recycling mechanism, ensuring that even the most voracious objects in the universe are subject to the same quantum rules that govern everything else. Visualizing this is key to grasping its elegance. Picture a massive black hole against the backdrop of space. It isn't just a dark, featureless sphere. Its event horizon would appear to be shimmering with a faint, ethereal glow, the Hawking radiation being born from the quantum foam at its boundary. It would be a halo of creation and destruction, a visible manifestation of the virtual particle pairs being torn asunder. This glow is unimaginably faint for a large black hole, far too weak for our current telescopes to detect, but for a theoretical micro-black hole in its final moments, this glow would be an intense, high-energy beacon signaling its impending demise. This image beautifully illustrates the deep connection between the largest and smallest scales in physics, showing how the frantic activity at the Planck scale can ultimately determine the destiny of an object whose gravity can trap light itself. But the quantum foam's influence might not be confined to the exotic realms of black holes and cosmic expansion. It could be subtly altering the very laws of physics we consider immutable. This brings us to our 11th theory, a truly provocative idea that challenges one of Einstein's most sacred tenets. What if the speed of light in a vacuum is not a constant? The theory of foam-induced light speed variation proposes that the frothy, chaotic nature of spacetime at the Planck scale acts like a kind of cosmic molasses, causing light to travel at slightly different speeds depending on its energy. According to this radical notion, the vacuum of space is not a perfect medium. It's a grainy, turbulent sea, and higher energy photons, like powerful gamma rays, would interact with this foam more strongly than their lower energy counterparts. Think of it like wading through water. If the water is perfectly still, you can move through it at a steady pace. But if the water is full of churning foam and bubbles, your progress becomes more turbulent. And if you're moving faster and with more energy, you might splash against the foam more noticeably, experiencing a tiny, almost imperceptible drag. In this analogy, the highest energy light in the universe is constantly splashing against the quantum foam, and that interaction could minutely slow its progress across the cosmos. This concept strikes at the heart of Einstein's special relativity, which is built upon the foundational principle that the speed of light in a vacuum, denoted by c, is the same for all observers and for all wavelengths of light. It is the ultimate constant, the unwavering ruler against which we measure space and time. If this constancy is merely an approximation that breaks down at the Planck scale, it would force a profound revision of modern physics. The implications ripple out across everything from our understanding of causality to the possibility of a preferred reference frame in the universe. It suggests that the seemingly smooth, uniform stage of relativity is in fact a macroscopic illusion, and that the true, underlying spacetime has a texture that selectively affects how different things move through it. How could we possibly detect such a minuscule effect? This is where the narrative transforms into a grand, cosmic detective story, with astronomers using the universe itself as their laboratory. The key is to observe the most energetic and distant light sources we can find. When a distant quasar, a galaxy with a hyperactive supermassive black hole at its core, erupts in a cataclysmic flare, it can unleash a torrent of gamma-ray photons across a vast spectrum of energies. These photons then embark on a multi-billion-year journey across the universe to reach our telescopes here on Earth. According to the standard model of physics, all these photons, regardless of their energy, should travel at exactly the same speed. They should all arrive at exactly the same time, like a perfectly synchronized cosmic parade. But if the quantum foam introduces even a tiny energy-dependent delay, the highest energy photons would arrive a fraction of a second later than their lower energy siblings after their epic journey. Scientists have been meticulously analyzing data from powerful instruments like the Fermi Gamma Ray Space Telescope and ground-based observatories like MAGIC, searching for exactly this kind of lag. They look for flares from quasars billions of light-years away, carefully timing the arrival of gamma rays across different energy bands. A confirmed detection of such a time delay would be like finding a fingerprint of the quantum foam, a direct observational clue that the fabric of spacetime is indeed grainy. The search is incredibly challenging, as the expected time difference is almost unimaginably small, perhaps mere milliseconds over a journey of billions of years. It's a testament to the precision of modern astrophysics that we can even attempt such a measurement, hunting for a whisper of Planck-scale physics in the most powerful explosions in the universe. Finding evidence for a variable speed of light would do more than just confirm the foamy nature of spacetime. It would fundamentally reshape our understanding of the constants of nature. The fixed value of c is woven into the very equations that describe reality. If it is not truly constant but merely appears so in our low-energy, local environment, then other constants might be similarly variable. This opens the door to a far more dynamic and evolving cosmos, where the fundamental rules could have been different in the distant past or might change in the far future. It suggests that our universe's operating manual isn't written in permanent ink, but is rather a set of emergent properties that arise from the churning, probabilistic chaos of the quantum foam, a foundation that is not only alive with activity but also inconstant at its very core. While the quantum foam might seem to allow for the possibility of microscopic time travel through its wild fluctuations, there is a compelling argument that the universe has a built-in safety mechanism to prevent such paradoxes from ever becoming a reality. This brings us to our 12th theory, the chronology protection conjecture, a fascinating proposal put forth by Stephen Hawking. He suggested that the laws of physics, particularly as they operate within the quantum foam, actively conspire to prevent time travel to the past. Think of it not as a limitation of our technology, but as a fundamental law of nature, a cosmic rule that protects the sequence of cause and effect from being violated. Hawking famously quipped that the absence of tourists from the future is perhaps the strongest evidence that time travel is impossible. His conjecture provides a potential physical reason for why this must be so. The core of the idea lies in what would happen if someone tried to create a stable, traversable wormhole or any other configuration that could serve as a time machine. According to the mathematics of general relativity, such structures are theoretically possible. However, the moment you attempt to turn one into a closed time-like curve, a path through spacetime that loops back into its own past, the quantum foam would react catastrophically. The calculation goes like this. As the time machine is being activated, virtual particles would begin to travel through the loop. A single photon, for instance, could enter the time machine, travel into the past, and then emerge just in time to enter the machine again. It would then complete the same journey over and over, piling onto its previous self with each cycle. This creates a devastating feedback loop. The energy of the radiation circulating in the loop isn't just duplicated, it builds upon itself exponentially with every completed cycle. In a very short span of time, the energy density in the region would skyrocket towards infinity. The quantum foam, which is normally a seething but balanced sea of fluctuations, would be driven into a state of violent instability. The very fabric of spacetime would be stressed beyond its limits, and before any information or object could be sent back to change the past, the immense concentration of energy would either destroy the time machine itself or warp spacetime so severely that the closed loop could never form. The universe, in essence, would rather tear itself apart at the quantum level than allow a paradox to occur. This isn't about a grandfather paradox where you go back and prevent your own birth, creating a logical inconsistency. The chronology protection conjecture operates on a more fundamental, physical level. It suggests that the universe enforces causality through sheer energetic brute force. The quantum vacuum itself becomes unstable in the presence of a causality-violating structure, and that instability acts as a physical barrier. It's as if spacetime possesses a kind of immune system. Any event that would threaten the linear progression of time triggers a catastrophic reaction that neutralizes the threat before it can materialize. The foam, in this view, is not just a passive foundation, it is an active guardian of chronological order. So, while the quantum foam may be filled with fleeting wormholes and fluctuating geometries that hint at temporal weirdness, Hawking's conjecture offers a compelling reason for why we are forever anchored to our own present. The universe seems to have a profound preference for a consistent, paradox-free history, and it uses the raw, unpredictable power of quantum fields to maintain it. The very same froth that allows for the creative spontaneity of virtual particles also possesses a destructive potential that safeguards the timeline, ensuring that the river of time flows in one direction only, protecting the story of the cosmos from ever being rewritten. But if the quantum foam in our universe is this turbulent, what if it's merely a single bubble in a far vaster, more turbulent ocean? This brings us to a theory that expands the scope of our reality to almost unimaginable proportions. Welcome to the idea of the multiverse, specifically the concept of eternal inflation, where our entire cosmos is just one bubble in a frothing, infinite cosmic foam of universes. In this breathtaking picture, the Big Bang wasn't a one-time, unique event that created everything from nothing. Instead, it was a local event within a much larger, eternally inflating meta-universe. Think of a pot of water on a rolling boil. Our universe isn't the pot, it's just one of countless bubbles forming, rising, and expanding in that boiling water. The quantum foam we've been exploring is the very substance from which new, entire universes can spontaneously nucleate and bud off, each with its own unique set of physical laws and constants. The engine for this endless creation is a hypothetical field known as the inflaton field. In the very early moments of our universe, this field is thought to have undergone a period of incredibly rapid expansion called inflation, which smoothed out our cosmos and made it so large and uniform. In the eternal inflation model, this process never truly stops everywhere at once. Most of the meta-universe remains in a state of hyper-fast eternal inflation. But within that raging energy sea, random quantum fluctuations can cause tiny patches to suddenly drop into a lower energy state, much like a bubble of steam forming in boiling water. When this happens, the energy released by that transition fuels a localized Big Bang, and that patch begins to inflate at a fantastic rate, spawning an entire new universe within the greater multiverse. Our universe is just one such bubble, and the quantum foam at its smallest scale might be the interface, the membrane through which this cosmic budding occurs. The implications of this are staggering. Each of these budding universes could have wildly different properties. In one, the strength of gravity might be 1,000 times stronger, causing stars to burn out in an instant. In another, the electromagnetic force might be too weak to form atoms, leaving a universe of scattered particles. Some universes might have more spatial dimensions, others fewer. The vast majority of these cosmic bubbles would be stillborn or sterile, utterly incapable of supporting any form of complexity, let alone life. We find ourselves in one of the rare Goldilocks universes where the constants are just right for galaxies, planets, and life to emerge. This offers a potential explanation for the incredible fine-tuning we observe, such as the cosmological constant problem. The value isn't fine-tuned for us. We simply exist in one of the rare universes where the numbers allow for our existence, a concept known as the anthropic principle applied on a multiversal scale. Visualizing this multiversal foam is a challenge for the imagination. Picture an infinite dark ocean representing the eternally inflating meta-universe. This ocean is not calm, it is a seething cauldron of unimaginable energy. Everywhere, without end, new bubbles of reality are constantly blooming into existence. They expand at speeds faster than light, their surfaces shimmering with the energy of their birth. Inside each one, an entire cosmos is unfolding, stars igniting, galaxies swirling, and perhaps in a precious few, life and consciousness awakening to wonder about its own origins. Some bubbles might even collide with others, leaving potential scars in the cosmic microwave background, while most drift eternally apart, separated by the ever-expanding inflationary ocean between them. Our entire observable universe, with its hundreds of billions of galaxies, is just a single, fleeting bubble in this infinite, frothing expanse. This theory profoundly changes our perspective on existence. It suggests that creation is not a past event but an ongoing, eternal process. The quantum foam is not just the fabric of our universe, it is the fertile ground from which an infinity of universes perpetually spring forth. There was no absolute beginning, and there may be no final end, just an endless cycle of cosmic birth, evolution, and potentially death, playing out across an infinite landscape. The search for a single, unified theory of everything for our universe might then be like trying to find the laws that govern the shape of a single snowflake in a blizzard. The fundamental rules of the meta-universe could allow for a breathtaking diversity of local, bubble-level laws. In this view, the quantum foam is the ultimate creative engine, a cosmic loom endlessly weaving an infinite tapestry of realities, most of which will forever remain beyond our sight, yet whose existence is hinted at in the very fabric of our own. This takes us from a multiverse of budding cosmic bubbles back to the very genesis of our own, to a theory that places the quantum foam at center stage in the most important event since the beginning, the moment of cosmic inflation. The theory that the foam itself was the origin of cosmic inflation proposes that the universe's initial, unimaginably rapid growth was not driven by some external, mysterious field, but was a direct and inevitable consequence of the physics of the primordial quantum foam. Picture the universe in its first fleeting moments, a realm of such incredibly high energy and temperature that the distinction between the forces of nature, gravity, electromagnetism, the strong and weak nuclear forces blurred into a single, unified superforce. In this primordial fireball, the quantum foam wouldn't have been a subtle, microscopic froth. It would have been the dominant feature of reality, a turbulent, macro-scale ocean of spacetime fluctuations. The entire cosmos was quantum foam. Within this seething chaos, a critical transformation was waiting to happen. As the newborn universe expanded and cooled, it underwent a series of phase transitions, much like steam condensing into water or water freezing into ice. The theory suggests that one of these transitions, a shift in the state of the quantum foam itself, unlocked a colossal reservoir of repulsive gravity. In this earlier, more symmetric state, the foam's inherent vacuum energy was at an extremely high level, and this energy, when plugged into Einstein's equations, generates a powerful gravitational repulsion. The moment the foam underwent its phase change, this repulsive force was unleashed, acting like a cosmic piston that drove every point in space away from every other point at a rate far exceeding the speed of light. A region of spacetime smaller than a subatomic particle was inflated in a fraction of a second into a volume larger than our entire observable universe today. The beauty of this idea is how elegantly it solves several of cosmology's most perplexing puzzles simultaneously. Take the horizon problem. When we look at the cosmic microwave background radiation, the faint afterglow of the Big Bang, we see that it has the same temperature in all directions to an astonishing degree of precision. This is deeply puzzling because in a universe expanding at a standard rate, these distant regions would never have had time to communicate and equalize their temperature. Inflation provides the perfect solution. Before inflation, that tiny patch of spacetime was small enough to be in causal contact, allowing it to smooth itself out into a uniform state. Then inflation blew this tiny, homogeneous region up to a cosmic size, preserving that uniformity across the vast scales we observe today. The foam, in this view, provided the engine that took a small, well-mixed sample of the early universe and stretched it into our entire cosmic landscape. Furthermore, this process didn't just create a smooth universe, it also planted the seeds for all future structure. The quantum foam is, by its very nature, probabilistic and fluctuating. Even as inflation was stretching space-time, these inherent quantum fluctuations in the foam were being stretched along with it, blown up from microscopic quantum ripples to macroscopic cosmic proportions. These minute variations in density became the gravitational seeds around which all the structure in the universe, galaxies, clusters, and superclusters, would later form through the relentless pull of gravity. The intricate cosmic web we see mapped out across the sky today, with its vast filaments of galaxies and immense voids, can trace its lineage directly back to those random, minuscule tremors in the primordial quantum foam. The largest structures in existence were born from the smallest possible vibrations, a direct link between the quantum and the cosmic forged in the first instant of time. This theory offers a compelling narrative that unites the very small with the very large in a single, continuous story. It suggests that the inflationary epoch wasn't an ad hoc addition to the Big Bang theory, but a natural and dynamic phase in the evolution of spacetime itself, driven by the changing properties of its fundamental fabric. The same chaotic, energetic foam that we now infer from particle collisions and theoretical models may have been the very agent that sculpted our universe into the vast, structured, and uniform cosmos we inhabit. It transforms the quantum foam from a passive, microscopic texture into an active, cosmic sculptor, whose brief but spectacular moment of repulsive power set the stage for the next 14 billion years of cosmic evolution and ultimately made our complex, life-bearing universe possible. If the quantum foam truly is a chaotic sea of possibility, then how does anything ever become definite? How does a particle decide where to appear when we measure it? One of the most audacious answers comes from a theory that reimagines the flow of time itself, connecting the foam directly to the mysterious process of quantum collapse. This is the transactional interpretation of quantum mechanics, a perspective that suggests the universe settles on a single reality through a kind of handshake across time, a negotiation where the quantum foam acts as the bustling marketplace where these deals are struck. At its heart, this interpretation proposes that the famous quantum wave function, which describes all the possible states of a particle, emits waves not just forward in time but also backward. These are called offer waves and confirmation waves. An offer wave travels forward from the moment a particle is emitted, exploring all possible paths just as in the standard quantum view. But then, from the future, from the moment a measurement is made or an interaction occurs, a confirmation wave travels backward in time, meeting the offer wave. It is only when these two waves, one from the past and one from the future, meet and reinforce each other that a tangible event actually happens in the present. The particle clicks in a detector or a photon strikes a specific spot on a screen because a transaction across time has been successfully completed. This is where the quantum foam becomes the essential medium for this breathtaking process. The foam, with its turbulent sea of microscopic wormholes and fluctuating geometries, provides the physical substrate through which these offer and confirmation waves can travel and interact. Think of the foam as a cosmic network of fibers, a complex telecommunications grid operating at the Planck scale. The offer wave moving forward doesn't travel on a smooth, classical path. It propagates through this grainy, foamy medium, its path influenced by the ever-changing topography of spacetime itself. Similarly, the confirmation wave moving backward navigates this same labyrinth. The foam's structure doesn't just allow for this two-way communication. It may be the very reason it is necessary. The chaotic, probabilistic nature of the foam means that establishing a definitive outcome requires a kind of consensus building across the timeline, a ratification from the future that confirms one specific possibility out of the infinite many. This interpretation casts the famous double-slit experiment in a completely new and dramatic light. In the standard experiment, a single particle fired at a barrier with two slits seems to pass through both simultaneously, creating an interference pattern on the detector screen behind it, a pattern that only makes sense if the particle behaved as a wave. In the transactional view, here's what happens. The particle's offer wave travels forward and passes through both slits, just as in the standard explanation. But then, from every possible point on the detector screen where the particle could land, confirmation waves travel backward in time. These waves go back through the slits and seek out the original offer wave. The point on the screen that sends back the confirmation wave that perfectly reinforces the offer wave is the one where the transaction is completed. The particle manifests there, and the interference pattern emerges as a statistical result of all these completed transactions over many trials. The foam is the medium that facilitates this entire, non-local conversation, allowing waves from the future to influence events in the present. This perspective offers a radical resolution to the long-standing mystery of quantum collapse. In the conventional Copenhagen interpretation, the wave function mysteriously collapses upon measurement, but the theory provides no mechanism for how or why this happens. The transactional interpretation provides a dynamic, physical picture. Collapse isn't a mysterious, instantaneous event. It is the culmination of a physical process, a transaction finalized through the interaction of waves in the quantum foam. This process is inherently acausal from our linear perspective, as the future seems to be influencing the past, but it creates a consistent, self-correcting loop that always results in a single, definite outcome that obeys the conservation of energy and momentum. The foam, therefore, is not a passive backdrop but an active participant in the creation of reality, a dynamic arena where time's arrow becomes a two-way street, and the universe continuously defines itself through a relentless dialogue between what was and what will be. Yet for all its elegance, the transactional interpretation is just one possible answer to one of the most persistent riddles in all of physics. Why does the quantum world of multiple possibilities resolve into the single, definite reality we actually experience? This brings us to our 16th theory, a profound idea that suggests the answer lies not in our observations, but in the very fabric of the cosmos. This is the potential role of the quantum foam in solving the infamous measurement problem. At its heart, the measurement problem asks why we never see a cat that is both dead and alive, or an electron in two places at once, even though the mathematics of quantum mechanics insists these superpositions are real. Something must be causing the wave function, the description of all possible states, to collapse into one specific outcome. The quantum foam, with its inherent chaotic turbulence, might just be that something, providing a physical mechanism that constantly nudges the quantum world toward classical definiteness. The core of this idea is that the vacuum of space is never truly quiet or still. The quantum foam is a maelstrom of fluctuations, and these tremors in spacetime itself could be continuously interacting with every single particle in the universe. In this view, a particle isn't just existing in a superposition. It's constantly being jostled and buffeted by the seething energy of the foam. This isn't a violent collision, but a subtle, relentless background noise. For very small systems, like a single electron, this noise is too faint to have much effect, and the particle can happily exist in its spread-out, wave-like state. But for larger objects composed of many trillions of atoms, the collective effect of this spacetime jitter becomes overwhelming. The foam's random kicks effectively drown out the quantum weirdness, forcing the object to pick a single, classical state. The transition from the quantum realm to the classical world wouldn't require a conscious observer. It would be an inevitable, physical process driven by the universe's own turbulent foundation. This concept is powerfully formalized in a class of theories known as dynamical collapse models, with one of the most prominent being continuous spontaneous localization, or CSL. The name itself is revealing. Continuous means it's always happening, spontaneous means it happens on its own, and localization means it makes things settle into one place. CSL proposes a tiny, universal field that permeates all of space, causing every particle to undergo an exquisitely gentle but persistent random collapse. The rate of this collapse is incredibly slow for a single electron. It might take hundreds of thousands of years to localize, but for a macroscopic object like a cat or a measuring device, the effect is amplified by the sheer number of particles. All those trillions of individual tiny collapses add up in an instant, ensuring the entire object is always in a definite state. In this framework, the quantum foam isn't just a passive environment. It is the physical manifestation of this randomizing field, the source of the noise that continuously resets reality from the bottom up. To visualize this, imagine a tiny, perfectly balanced needle standing on its point. In a perfectly still, silent room, it could theoretically remain balanced forever, existing in a superposition of every possible falling direction. But in the real world, that needle is constantly being jostled by random air molecules, vibrations from the floor, and sound waves. It's an unstable equilibrium, and the slightest nudge will cause it to tip over into one definite direction. In the CSL picture, the quantum foam is like that random, ambient noise. A subatomic particle is the needle in a nearly silent room. It can maintain its delicate superposition for a long time. But a cat is like that needle in the middle of a rock concert. The relentless barrage of kicks from the spacetime foam makes it impossible for it to remain in a blurred state, forcing it to be either definitively alive or definitively dead at every single moment. The collapse isn't an event, it's a constant process of the universe reminding large objects how to behave. The implications of this are staggering, as it would mean that the classical world we perceive is an emergent property of a deeper, noisier quantum reality. There is no mysterious division between the quantum and classical realms. There is only a smooth transition governed by size and the constant interaction with the spacetime foam. This also provides a potential bridge between the probabilistic rules of quantum mechanics and the deterministic feeling of our everyday world. The outcomes are still random, but the process of achieving them is driven by a real, physical mechanism woven into the cosmos, rather than by the act of human consciousness or measurement. It transforms quantum mechanics from a theory about our knowledge of the world into a theory about the world itself. A theory where the frenetic activity of the quantum foam is the invisible hand that sculpts definite reality from a sea of shimmering potential. If the transactional interpretation gives us a marketplace for reality and collapse models give us a cosmic noise floor, then our next theory asks us to reconsider the very coordinates we use to map the universe. Imagine trying to pinpoint the exact location of a single bubble in a pot of boiling water. The moment you think you have it, it pops or merges with another, and its identity is lost. This isn't far from the reality proposed by our 17th theory, non-commutative geometry, a profound mathematical framework suggesting that at the Planck scale, the very concept of a specific location becomes fundamentally meaningless, replaced by a fuzzy, uncertain geometry that is the quantum foam. At its heart is a deceptively simple but radical idea. In this domain, the order in which you measure things matters profoundly. In our everyday world, if you're asked to describe the location of a book on a table, it doesn't matter if you give its distance from the north edge first and then the east edge or vice versa. The two descriptions, its x and y coordinates, are independent, they commute. But in the non-commutative world of the quantum foam, this is no longer true. Measuring a position in one direction and then another could yield a different result than if you had measured them in the reverse order. This isn't just a mathematical curiosity. It implies that spacetime itself has a built-in uncertainty principle, much like the one we know from quantum mechanics for position and momentum. You cannot simultaneously know both the x and y coordinates of a point in spacetime with infinite precision. The more sharply you try to pin down one coordinate, the more blurred and uncertain the other becomes. This leads to a picture of spacetime not as a smooth, infinitely divisible grid, but as a fuzzy, blurry tapestry where individual points lose their identity. Think of a finely woven piece of fabric. From a distance, it appears smooth and continuous. But if you press your face right up against it, the individual threads become apparent, and the precise point you're looking at becomes difficult to define. Is it on this thread or the one next to it? In non-commutative geometry, the universe is this fabric, and the quantum foam is the inherent fuzziness that emerges when you look closely enough. The frantic bubbling and fluctuations we've discussed are not happening in space. They are the manifestation of this fundamental non-commutativity, this deep-seated refusal of spacetime to be pinned down to a single, precise address. The mathematical language used to describe this is as beautiful as it is complex, replacing the familiar commutative numbers of our everyday geometry with mathematical objects called matrices or operators that do not commute. In this framework, the spacetime we experience is a sort of average, a classical shadow of a far more intricate, non-commutative reality operating at the Planck scale. This approach provides a powerful new perspective on the unification of forces. Just as Einstein showed that gravity is the curvature of smooth spacetime, non-commutative geometry suggests that the other fundamental forces, the electromagnetic, weak, and strong nuclear forces, might also be manifestations of geometry, but of this new, fuzzy quantum geometry. The different particles and forces we observe could be different vibrational modes or excitations of this non-commutative tapestry, all emerging naturally from its intrinsic structure without the need for additional ad hoc fields. To make this abstract idea more concrete, consider the humble atom. In the early 20th century, Niels Bohr proposed a model where electrons orbit the nucleus in specific, discrete shells. This was a radical departure from the classical picture of a planet orbiting a star, where any orbit is possible. Bohr's quantized orbits were the first sign that at tiny scales, reality becomes granular. Non-commutative geometry does for spacetime what quantum mechanics did for the atom. It imposes a fundamental granularity and fuzziness on the fabric of reality itself. You cannot have a spacetime point smaller than a certain scale, just as an electron cannot exist between two allowed energy shells. The foam, then, is the visual and physical expression of this granularity, a direct consequence of the fact that the universe's underlying coordinate system operates by a different, more uncertain set of rules than the ones we use to navigate our daily lives. It reveals a cosmos where precision has a limit, and the certainty of location is an illusion that shatters when we peer into its deepest foundations. Now, if the quantum foam serves as the cosmic noise that defines our reality and a fuzzy tapestry that refuses precise location, we must ask, what happens when this dynamic fabric encounters the most absolute prison in the universe, a place where even light cannot escape? This brings us to a theory that forges an iron link between the frantic chaos of the microscopic and the serene, deadly calm of the macroscopic. It's the profound connection between the quantum foam and black hole thermodynamics, specifically through the lens of the Bekenstein-Hawking entropy. This idea tells us that the surface of a black hole, its event horizon, is not a smooth, featureless boundary. Instead, it is a frenzied, pixelated membrane, and the quantum foam is the physical manifestation of the incredible amount of information stored there. The entropy of a black hole, a measure of its hidden information or disorder, is not proportional to its enormous volume, as you might intuitively guess, but to the surface area of its event horizon. This was Jacob Bekenstein's revolutionary insight, later solidified by Stephen Hawking's work on radiation. It means that all the information about every star, planet, and atom that has ever fallen into the black hole is not lost in the mysterious singularity at its center. Instead, it is meticulously encoded on its two-dimensional surface, and the quantum foam provides the microscopic pixels that make up this cosmic hard drive. To understand why this is so startling, consider what entropy means in everyday life. If you shatter a vase, the scattered pieces have a much higher entropy than the intact vase. There are vastly more ways to arrange the broken fragments than there were for the single assembled object. A black hole is the ultimate example of this. It is the most entropic object possible for its size, the end state of disorder. The Bekenstein-Hawking formula calculates this entropy, and the result is staggering. A black hole with an event horizon the size of a typical city block would contain more entropy than all the particles in the entire observable universe. This is an almost incomprehensible amount of hidden information. The question then becomes, what are the microscopic, physical degrees of freedom that account for this immense number? What is the stuff that is so disordered? The leading candidate is the quantum foam itself. The event horizon is not a passive wall. It is a seething layer where the foam's characteristic fluctuations, the popping virtual particles, the fleeting wormholes, the vibrating loops of space are pushed to an extreme. Each tiny Planck-sized area on the horizon can exist in a vast number of different quantum states, and the sum total of all these possible configurations across the entire surface equals the black hole's colossal entropy. This transforms our picture of a black hole from a simple, dark void into the most complex object in existence. It's not an empty pit, it's a bustling, two-dimensional surface buzzing with quantum activity, a hologram storing a universe's worth of data. The foam at the horizon is the physical embodiment of this data storage. Every time a bit of matter falls in, the event horizon grows slightly, providing just enough new surface area to perfectly encode the information contained in that matter, pixel by pixel onto the foamy canvas. This resolves the infamous information paradox that troubled Hawking for decades. He initially thought that information swallowed by a black hole was lost forever, which would violate a core principle of quantum mechanics. But if the information is never truly inside the black hole, but is instead painted on its surface in the language of the quantum foam, then it can, in principle, be preserved and even slowly radiated back out during the Hawking evaporation process. The foam, therefore, acts as the universe's ultimate archivist, ensuring that not a single bit of information is ever truly destroyed, even in the face of total gravitational collapse. This revelation elevates the quantum foam from a curious microscopic phenomenon to a central player in the quest for a theory of quantum gravity. The Bekenstein-Hawking entropy formula is one of the very few solid bridges we have between the worlds of general relativity and quantum mechanics. Any candidate theory of quantum gravity, be it string theory or loop quantum gravity, must be able to derive this formula from first principles by counting the specific microscopic states of the spacetime fabric. The fact that the entropy is proportional to the area, not the volume, is a powerful clue that the true, fundamental degrees of freedom of the universe reside on a lower dimensional surface, just as the holographic principle suggests. The furious activity of the quantum foam on the boundary is what creates the illusion of a three-dimensional interior. In this view, a black hole isn't storing information in its volume. It is projecting it from its surface, and the foam's intricate, ever-changing structure is the mechanism that makes this cosmic projection possible, tying together the fate of information, the nature of gravity, and the very fabric of spacetime into one coherent, if deeply mysterious, whole. Building from the idea of a bustling information archive at a black hole's event horizon, we now turn to a theory that reimagines the very substance of this cosmic fabric. What if the quantum foam isn't just a chaotic froth, but a state of matter so exotic that it flows without any friction whatsoever? This is the captivating proposal that spacetime itself, in its most fundamental form, could be a superfluid. Imagine a cosmic fluid with zero viscosity, where turbulence and resistance simply do not exist. On Earth, we can create such substances like superfluid helium, which can climb the walls of its container and form impossibly thin films. If the fabric of the universe shares these properties at the Planck scale, it would revolutionize our understanding of how everything from particles to forces come into being. The appeal of this analogy lies in its potential to explain some of the universe's most persistent mysteries. One of the biggest puzzles in cosmology is the observed uniformity of the cosmos. The temperature of the cosmic microwave background is nearly identical in all directions, suggesting that distant regions of the universe were once in contact. In the standard Big Bang model, this is difficult to explain, as these regions would not have had time to communicate. However, if the early universe was filled with a superfluid quantum foam, the story changes dramatically. A superfluid can support sound waves and other excitations that travel with exceptional efficiency, potentially allowing for the rapid smoothing out of any temperature differences in the primordial cosmos. This superfluid medium could have acted as a cosmic synchronizer, ensuring the entire observable universe started from the same initial conditions without requiring any mysterious, faster-than-light influences. Perhaps the most profound implication of the superfluid foam idea is how it could explain the origin of particles and forces themselves. In the world of condensed matter physics, the defects and excitations within a material can behave exactly like particles. For instance, in a superfluid or a crystal, a tiny vortex or a dislocation isn't just an imperfection. It can move, interact, and obey mathematical rules that are eerily similar to the laws governing subatomic particles. In the superfluid spacetime model, an electron or a quark might not be a fundamental point-like object. Instead, it could be a tiny, stable whirlpool or a knot in the flowing superfluid of the quantum foam. The different properties of particles, their mass, charge, and spin, could simply be different types of topological defects, various ways in which the smooth fabric of spacetime has become tangled or twisted at the microscopic level. This perspective offers a stunningly unified vision of reality. The The four fundamental forces we know, gravity, electromagnetism, and the strong and weak nuclear forces, might also emerge from the dynamics of this superfluid substrate. Just as the collective behavior of water molecules gives rise to properties like surface tension and pressure waves, the collective excitations of the superfluid foam could manifest as the force carriers we observe. A photon, the particle of light, might be a ripple in this fluid. The gravitational force could be an emergent consequence of the fluid's pressure and density, much like how Einstein's general relativity describes gravity as the curvature of a medium. In this view, the entire zoo of particles and forces is not a collection of separate, fundamental entities, but a spectrum of different behaviors exhibited by a single, underlying substance, the superfluid quantum foam. This theory provides a powerful bridge between the physics of the very large and the very small, using the well-established principles of condensed matter physics to illuminate the mysteries of cosmology. We don't need to invent entirely new, abstract dimensions or particles. We can look to the complex behaviors of fluids and solids we already understand for clues about the universe's operating system. The concept that everything we see is a kind of excitation or defect in a deeper, smoother reality is both elegant and humbling. It suggests that the universe at its heart is a unified and coherent whole, and that the apparent complexity of the quantum world is simply the rich and varied music played on the superfluid strings of spacetime itself. This radical shift in perspective brings us to a theory that stands as one of the most profound in modern physics, an idea that turns our understanding of reality inside out. This is the emergent spacetime paradigm, a revolutionary framework suggesting that the space we inhabit and the gravity we feel are not fundamental ingredients of the universe at all. Instead, they are secondary phenomena, collective illusions that emerge from a far more basic and bustling layer of quantum reality. Think of it like the temperature of a gas. We can measure a single temperature, but that reading doesn't belong to any one atom. It emerges from the frantic, chaotic motion of countless molecules. In the same way, the smooth, continuous stage of spacetime and the force of gravity may be thermodynamic consequences, large-scale behaviors that arise from the complex interactions of countless underlying quantum building blocks. So, what are these fundamental building blocks if not spacetime itself? The answer lies in the strange and powerful phenomenon of quantum entanglement. In this emergent view, the most basic units of reality are not tiny strings or loops, but bits of quantum information or qubits, and the intricate web of entanglement that connects them. Picture the universe not as a container, but as a vast cosmic network, with each node representing a quantum bit. Now, imagine that when two of these qubits become entangled, a fundamental link is forged between them. It's not a link through space. The link itself defines the very notion of spatial proximity. The more entangled two qubits are, the closer they are in the emergent geometric space. From this dense, interconnected network of quantum correlations, the very geometry of spacetime is woven into existence. The three-dimensional world we navigate is, in essence, a holographic projection of this underlying entanglement architecture. This is where the quantum foam finds a stunning new identity. In this paradigm, the foam's characteristic churning and bubbling is not the random boiling of a primordial substance, but the visible, energetic signature of this underlying quantum computer at work. The foam is the processor. Each fleeting virtual particle pair, each microscopic wormhole fluctuation, is a computational operation, a quantum gate being applied, a correlation being established or broken, a piece of the cosmic calculation being executed. The frantic activity at the Planck scale is the universe constantly processing information, updating the entanglement relationships between its fundamental qubits, and in doing so, dynamically constructing the fabric of reality moment by moment. The foam is the visual manifestation of cosmic computation in progress. This perspective elegantly reframes the force of gravity. In Einstein's general relativity, gravity is the curvature of spacetime, a geometric effect. In the emergent paradigm, this curvature is not a primary property but a consequence of the entanglement structure of the underlying quantum network. A massive object like the Sun, by its very presence, alters the entanglement patterns in its vicinity. It effectively reorganizes the quantum information network, and this reorganization projects into our macroscopic reality as the curved geometry we interpret as a gravitational field. The reason planets orbit stars is not because they are following curved paths in a pre-existing stage, but because the fundamental quantum connections that define that stage have been reconfigured by the star's mass. Gravity becomes an entropic force, a tendency for the system to maximize its quantum complexity, much like how heat flows to maximize disorder. The implications of this are truly staggering, suggesting that our universe might literally be an ongoing quantum computation. The laws of physics we have painstakingly uncovered the standard model, general relativity, are not the source code. They are the high-level operating system, the emergent laws that govern the behavior of this cosmic software. The quantum foam processor runs on rules we are only beginning to glimpse, and the universe we perceive is the output, the result trillions upon trillions of qubits processing information in a coordinated, stable way. This doesn't mean our reality is a simulation in the sense of being created by some external programmer. It means that the very nature of existence is intrinsically computational. To be real is to be part of a vast, self-organizing quantum information network. This view also provides a fresh lens through which to see some of our previous theories. The holographic principle, for instance, becomes a natural consequence. If our three-dimensional world emerges from a quantum network, then the information content of a volume of space is necessarily bounded by the information capacity of its two-dimensional boundary, because that's where the fundamental qubits actually live. The Bekenstein-Hawking entropy of a black hole is simply a count of the number of entangled qubits on its event horizon, the surface that forms the processing boundary for that region of spacetime. Even the cosmological constant problem might find a resolution here, as the near-zero value of dark energy could correspond to a universe whose quantum computational network is in a particularly stable and low-energy state, optimally configured for the long-term evolution that makes our existence possible. In the end, the emergent spacetime paradigm offers a breathtakingly unified vision where the frantic foam, the pull of gravity, and the vast expanse of the cosmos are all different facets of a single, profound truth, that the universe is, at its heart, a grand and continuous act of quantum information processing. But this radical reimagining of space as an emergent, computational construct forces us to confront a pillar of modern physics that has stood unshaken for over a century. What if the very symmetry that underpins Einstein's relativity is not a perfect law, but merely an excellent approximation that finally fractures when we probe the furious granularity of the foam? This brings us to our 21st theory, a concept that strikes at the heart of Einstein's legacy, the possibility that quantum foam induces a violation of Lorentz invariance. This foundational principle states that the laws of physics are exactly the same for all observers moving at constant velocity relative to each other. It's the reason why the speed of light in a vacuum is constant for everyone, whether you're standing still or racing away in a spaceship at 99% of light speed. It ensures that the universe has no preferred frame of reference, no cosmic center stage. Yet, if spacetime is truly a seething, granular foam at its core, this perfect symmetry might develop tiny, telltale cracks. The logic here is as compelling as it is simple. Imagine the smooth, uniform space of relativity as a perfectly calm, glassy sea. On this sea, all waves, regardless of their origin or direction, travel with the same unwavering speed. Now imagine that this sea is not truly smooth, but is instead filled with an invisible, fine mist. In principle, this mist is the same in all directions, so it shouldn't affect the waves. But what if the mist is actually a foam, a churning collection of discrete bubbles? A very long, low-energy wave might not even notice the foam. It would glide over the tiny bubbles as if they weren't there. However, an incredibly short, high-energy wave would be constantly slamming into these individual granules. Its journey would become a turbulent dash, and crucially, the nature of that turbulence could depend on the wave's direction of travel relative to the foam's hidden granular structure. The foam would act like a cosmic diffraction grating, treating light of different energies and potentially different polarizations in slightly different ways, breaking the perfect symmetry that Lorentz invariance demands. The hunt for these minuscule violations has become one of the most thrilling detective stories in modern astrophysics, and the key witnesses are the most powerful particles in the universe, ultra-high-energy cosmic rays. These are not mere photons, they are protons and atomic nuclei accelerated to energies millions of times greater than anything achievable in our largest particle colliders. They streak across the universe, and according to pristine Lorentz invariance, there is a strict speed limit. A fundamental prediction of Einstein's theory, combined with our understanding of particle physics, is that these ultra-high-energy protons should not be able to travel very far. They should collide with the low-energy photons of the cosmic microwave background radiation, the leftover heat from the Big Bang, in a reaction that robs them of their energy. It's as if the universe is filled with a thin cosmic fog that gradually slows down these interstellar speedsters over distances of a few 100 million light-years. This is known as the Greisen-Zatseping-Kuzmin or Giesecke cutoff. Yet, here's the mystery. Our telescopes have detected a handful of these cosmic rays with energies that seem to defy this cutoff. They arrive at Earth with an energy that, according to our standard models, they should have lost long before reaching us. One potential explanation is that Lorentz invariance is subtly broken. In a foamy spacetime, the very rules governing particle interactions might be slightly different. The energy threshold for that critical collision with the microwave background photons could be shifted. A proton that should have been stopped could, in a Lorentz-violating universe, find a way to slip through the cosmic fog, traveling vastly greater distances to deliver its immense energy to our detectors. The detection of these super Giesecke cosmic rays could therefore be more than just a curiosity. It could be the first indirect fingerprint of the granular structure of spacetime, a sign that these ultimate travelers are interacting with the quantum foam in a way that gently bends Einstein's most cherished rule. Scientists are deploying an arsenal of other sophisticated tools to hunt for this effect. They scrutinize the light from distant gamma-ray bursts, looking for tiny energy-dependent delays in arrival time, exactly as we discussed with the variable speed of light. They study the spin of distant pulsars, searching for any gradual change in their rotation that could indicate an interaction with a preferred direction in space, a cosmic grain that would be anathema to relativity. Laboratory experiments here on Earth push the boundaries of precision, using atomic clocks and laser interferometers to see if the fundamental constants of nature change ever so slightly as our planet rotates and orbits the Sun, moving through the hypothetical quantum foam. While no smoking gun has been found, the very fact that we can pose these questions and design experiments to test them shows how far we've come. We are no longer just theorizing about the foam. We are actively probing it, using the entire universe as our laboratory to see if the most perfect symmetry we know is, in fact, an illusion that shatters upon the jagged, Planck-scale shores of reality. But to truly grasp the nature of the quantum foam, we need to understand what could possibly be frothing. This brings us to a beautifully classical idea born from one of the 20th century's greatest physicists, an idea that attempts to build reality from the most fundamental ingredients of all, pure light and geometry. Welcome to our 22nd theory, the Wheeler-Jans concept. Conceived by the legendary John Wheeler, the man who also gave us the terms black hole and quantum foam, a djinn is a hypothetical, self-gravitating knot of electromagnetic energy. Imagine a wave of light, a photon, but instead of racing through space at light speed, it's trapped. It's bent and twisted into a stable, swirling pattern, held together by its own gravitational pull. In Wheeler's vision, a powerful enough concentration of light energy would, through Einstein's general relativity, curve the spacetime around it. This curvature, in turn, would act like a mirror, bending the path of the light back onto itself, creating a closed loop. The light becomes its own gravitational prison, a shimmering, ethereal object built from nothing but oscillating energy, a djinn. The sheer elegance of this idea lies in its parsimony. Wheeler was searching for a way to construct particles from fields alone without needing to postulate additional, point-like substances. In the djinn model, what we perceive as a solid particle, like an electron, might not be a tiny billiard ball at all. It could be a fantastically complex, dynamic whirlpool of electromagnetic force, a stable djinn so tiny and persistent that it manifests all the properties of mass and charge. The mass wouldn't come from some mysterious stuff, but directly from the energy content of the confined light via Einstein's famous equation, E equals mc squared. The energy of the confined light is its mass. This provides a breathtakingly unified picture. The force of gravity, described by the curvature of space-time, and the electromagnetic force, described by the confined light wave, are no longer separate actors on a stage. They are partners in a delicate, self-sustaining dance, each one creating the conditions necessary for the other's existence. Now, place this concept into the turbulent context of the quantum foam. The foam, in Wheeler's own conception, is a seething chaos of virtual phenomena at the Planck scale. Within this froth, djinns could be the temporary, semi-stable structures that give the foam its texture. A virtual particle pair bubbling into existence might, for an infinitesimal moment, achieve the configuration of a microscopic djinn before dissipating. The foam wouldn't just be a featureless energy soup. It would be populated by these fleeting, self-gravitating waves, constantly forming, interacting, and vanishing. They would be the fundamental excitations of the space-time fabric itself, the atoms of the foam. In this view, the foam's chaotic nature arises because these djinns are inherently dynamic and probabilistic. Their stability is a matter of quantum chance, leading to the constant, flickering appearance and disappearance that defines the quantum vacuum. While the concept of a classical, perfectly stable djinn in flat space ultimately runs into theoretical issues, they tend to be unstable and would either dissipate or collapse. This doesn't invalidate Wheeler's profound insight. Instead, it pushes the idea into the quantum realm. The true potential of djinns may be realized only when quantum mechanics is fully integrated with gravity. In a quantum theory of gravity, the definition of a djinn could evolve. It might not be a single classical wave, but a coherent quantum state of the gravitational and electromagnetic fields, a soliton-like entity that is stable thanks to quantum effects. These quantum djinns could then be excellent candidates for the fundamental building blocks of matter, providing a concrete, physical model for how particles emerge from the fields that permeate spacetime. They represent a bridge between the pure geometry of general relativity and the probabilistic, field-based nature of quantum mechanics, suggesting that at the deepest level, everything is a manifestation of self-interacting curved energy. The implications of this are as far-reaching as they are beautiful. If djinns, or something like them, form the basis of the quantum foam and of particles themselves, then the entire universe is, in a very literal sense, a construct of light and gravity. The solidity of the chair you're sitting on, the warmth of the sun on your skin, the very neurons firing in your brain, all of it would be, at its core, a magnificent and complex arrangement of trapped, self-gravitating energy woven from the fabric of spacetime. This vision from Wheeler, now decades old, continues to inspire physicists because it points toward a universe of profound unity, where the distinction between the stage and the actors dissolves, and reality reveals itself as an intricate tapestry of self-sustaining dynamic geometry. But this delicate dance of trapped light and gravity in the foam leads us directly to one of the most persistent and puzzling mysteries in all of fundamental physics, a problem that strikes at the very heart of why our universe has the structure it does. This is the hierarchy problem, and it forces us to ask a deeply unsettling question. Why is gravity so unbelievably, almost embarrassingly, weak? To grasp the sheer scale of this discrepancy, consider a simple magnet, the kind you might stick to your refrigerator. That tiny magnet, using the electromagnetic force, can easily overpower the gravitational pull of the entire Earth, a planet weighing over 6 trillion kilograms, and lift a paperclip against it. This isn't just a small difference in strength. Gravity is weaker than the electromagnetic force by a factor of 1,000 trillion. That's a 1 with 36 zeros after it. It's as if all the other forces are roaring like hurricanes, while gravity is the faintest whisper, a force so feeble it seems completely out of place in the same universe. The hierarchy problem is the quest to understand why this vast chasm in strength exists, and remarkably, the frenetic nature of the quantum foam might hold the key to this cosmic imbalance. The problem becomes critically urgent when we consider the Higgs boson, the particle responsible for giving all other particles their mass. The mass of the Higgs is intimately tied to the energy scale of the quantum foam. In the seething quantum vacuum, virtual particles of unimaginably high energy are constantly popping in and out of existence. These include hypothetical particles linked to a grand unified force with energies 1 trillion times greater than what our largest colliders can probe. According to quantum field theory, these ultra-heavy virtual particles should contribute to the Higgs mass, driving its value up to their own incredibly high energy scale, which is perilously close to the Planck energy where the quantum foam reigns. If this were allowed to happen unchecked, the Higgs mass would skyrocket, and in turn, the masses of all fundamental particles would become astronomically large. Electrons would become as heavy as baseballs, and atoms would instantly collapse. The universe as we know it, with its complex chemistry and potential for life, would be impossible. The fact that we exist and that the Higgs mass is relatively light means that some mysterious mechanism must be at work, cancelling out these enormous quantum corrections with breathtaking precision, leaving behind the tiny residual we observe. It's as if an enormous number of massive particles are constantly pushing the Higgs mass toward an impossibly high cliff, but an invisible hand is holding it back with exactly the right amount of counterforce, and we have no idea what that hand is. This is where one of the most celebrated proposals in modern physics enters the stage: supersymmetry. This elegant theory offers a potential solution directly tied to the foam's hidden structure. Supersymmetry posits that for every known particle in the standard model, every electron, quark, and photon, there exists a superpartner, a hidden shadow particle. An electron would have a selectron, a quark would have a squark, and so on. The magic of this proposal is in the mathematics. The quantum corrections to the Higgs mass from known particles are positive and huge, threatening to drive its value to the Planck scale. But the corrections from their superpartners are negative, and if the theory is perfectly symmetrical, exactly equal in magnitude, they would cancel each other out with perfect mathematical precision. The result is a protected, stable Higgs mass that remains light, effectively insulating the low-energy world we inhabit from the violent, high-energy chaos of the quantum foam. The foam's immense energy is still there, bubbling away, but its influence on the masses of particles is perfectly neutralized by this cosmic symmetry, resolving the hierarchy problem in one elegant stroke. Yet, for all its mathematical beauty, nature has so far refused to cooperate with this simple picture. If supersymmetry were an exact symmetry, these superpartners would have the same mass as their standard model counterparts, and we would have detected them long ago. They are nowhere to be found. This means that if supersymmetry is a property of our universe, the symmetry must be broken, and these shadow particles must be tremendously heavy, beyond the reach of our current particle accelerators. This breaking of supersymmetry reintroduces the hierarchy problem in a new, more subtle form. We now must explain why the breaking scale itself is so low, why the superpartners are not so incredibly massive that they fail to cancel the quantum corrections. The search for these particles is one of the primary missions of the Large Hadron Collider, and their continued absence has forced physicists to consider other, even more exotic, possibilities that might be at play within the foam. One such radical idea involves the very dimensions of space itself. In some string theory and brane world scenarios, the weakness of gravity might not be fundamental, but rather an illusion caused by gravity leaking out into extra, hidden spatial dimensions. Imagine our universe as a three-dimensional membrane or brane floating within a higher dimensional bulk. The electromagnetic, strong, and weak forces might be stuck to our brain, confined to our three-dimensional world. Gravity, however, as the curvature of spacetime itself, could permeate all dimensions. While the other forces are concentrated and thus appear strong in our world, gravity's influence is diluted as it spreads out into these extra dimensions. The quantum foam in this picture would be a higher dimensional phenomenon, its true ferocity only apparent from a cosmic perspective outside our brain. What we perceive as the incredibly weak force of gravity in our three-dimensional home might, in the full higher dimensional reality, be just as strong as the other forces. The hierarchy problem is then transformed from a question of why is gravity weak to why are the extra dimensions so large, a puzzle that may find its answer in the dynamics of how our cosmic membrane formed and evolved within the primordial foam. Ultimately, the hierarchy problem serves as a stark reminder of how little we understand about the deepest layers of reality. It exposes a profound sensitivity in the laws of physics, where the existence of a complex, life-bearing universe depends on an exquisitely fine-tuned cancellation of effects originating in the quantum foam. Whether the solution lies in supersymmetry, extra dimensions, or a concept we have yet to imagine, this puzzle forces us to look beyond our current theories. The incredible weakness of gravity, which we experience every time we lift an arm or jump into the air, may be the most important clue we have, a direct message from the Planck scale foam, telling us that the true nature of the cosmos is far richer and more interconnected than the forces we currently recognize. Of course, the constant seething activity of the quantum foam offers a potential physical answer to one of the most enduring and bizarre puzzles in all of quantum mechanics: the moment a particle's many possible states suddenly snap into one definite reality. This is the infamous measurement problem, and it asks why we never actually witness a cat that is both dead and alive, or an electron in two places at once. The mathematics insists these superpositions are real, yet our experience is always of a single, concrete outcome. What if the solution isn't found in the elusive nature of human consciousness, but in the relentless, chattering noise of the spacetime foam itself? Imagine trying to balance a needle perfectly on its point in an utterly silent, motionless room. In theory, it could remain in that precarious, undecided state indefinitely. But in the real world, that needle is constantly bombarded by invisible forces, the random jostling of air molecules, the subtle vibrations from the floor, the faintest of sound waves. It's an unstable equilibrium, and the slightest nudge will inevitably cause it to tip over into one definite direction. In this analogy, the quantum foam is that ever-present ambient noise. A subatomic particle is the needle in a nearly perfect vacuum. It can maintain its delicate superposition for a remarkably long time. But as objects get larger and more complex, the collective effect of trillions upon trillions of these tiny, random kicks from the foam becomes overwhelming. forcing the entire system to choose a single classical state. This idea is powerfully formalized in a class of theories known as gravitational decoherence. This specific model proposes that it is the foam's own tiny, fluctuating gravitational field that acts as the universal measurement device. Think about it, every single fluctuation in the quantum foam, every virtual particle pair that bubbles up, every microscopic wormhole that forms and vanishes, represents a minuscule ripple in the gravitational field. According to Einstein, gravity is the curvature of spacetime, so these ripples are literally tremors in the fabric of reality itself. Now, consider an object in a quantum superposition, say an atom that is in two slightly different locations at once. Each location corresponds to a slightly different gravitational field. In the gravitational decoherence model, the frantic, random gravitational fluctuations of the foam are constantly, unwittingly, feeling these different configurations. They interact with the superposition, and in doing so, they constantly gather information about it. This persistent, involuntary interaction with the environment, even an environment as ethereal as the quantum vacuum, destroys the delicate quantum coherence. It's as if the universe is constantly taking a sloppy, low-resolution picture of the system, and with each snapshot, the fuzzy quantum possibilities are forced to resolve into a single, sharp classical fact. The foam doesn't need to be measured by us. It is itself a continuous measurement process, a natural mechanism that tirelessly enforces the classical rules we experience. The implications of this are profound, as it would mean the transition from the quantum to the classical world isn't a mysterious boundary triggered by human observation. Instead, it's a smooth, physical process governed by size and the constant interaction with the spacetime foam. For a single electron, the foam's gravitational jitter is so weak that its superposition can survive for long periods, which is exactly what we see in laboratory experiments. But for a complex object like a dust grain, a virus, or of course a cat, the number of constituent atoms is so vast that the collective gravitational interaction with the foam is immense. The quantum weirdness is effectively drowned out by the cacophony of spacetime fluctuations, ensuring the object is always localized in one place with one definite state. This process, known as decoherence, explains why we never see large objects behaving quantumly. They are constantly being forced into classical definiteness by the buzzing background of their own existence within the dynamic foam. It provides a bridge between the two seemingly incompatible worlds of quantum probability and classical certainty, suggesting they are not separate realms at all, but two ends of a continuous spectrum shaped by the environment. What's truly fascinating is that this perspective transforms our view of the foam from a passive stage into an active participant in the creation of reality. The same chaotic, energetic foundation that gives rise to virtual particles and spacetime fluctuations also acts as the great clarifier, the mechanism that consistently collapses the wave function and delivers the definite world we perceive. This doesn't completely solve the so-called hard problem, of which specific outcome is chosen that still involves an element of quantum randomness, but it does explain why a single outcome must be chosen at all. The universe, through the intrinsic turbulence of its quantum foam, possesses a built-in tendency toward definiteness. It's a cosmic imperative that emerges from the bottom up, ensuring that for any system complex enough to be a part of our macroscopic experience, the shimmering potential of the quantum realm is continuously solidified into the unambiguous reality we navigate every day. This fundamental background static of the universe, a constant whisper of creation and annihilation, leads us to a theory that transforms this noise from a theoretical curiosity into a potential new observational frontier. The idea that the quantum foam generates a pervasive cosmic noise suggests that the universe is never truly silent, even in its most perfect vacuum. This isn't a noise you could hear with your ears. It's a primordial hiss etched into the fabric of spacetime itself, a stochastic background generated by the relentless probabilistic churning of the foam at the Planck scale. Every fluctuation, every virtual pair, every microscopic wormhole contributes to this universal static. For decades, this has been a purely theoretical concept, but we are now approaching an era where our technology might be sensitive enough to actually listen to this faint sizzle of reality, turning the phantom static of empty space into a revolutionary new window for observing the deepest laws of physics. The key to detecting this cosmic noise lies in understanding its most promising signature, its imprint on gravitational waves. When two black holes or neutron stars spiral together and collide, they send literal ripples through the fabric of spacetime, vibrations that travel at the speed of light. Our current observatories, like LIGO and Virgo, have opened this new sense, allowing us to hear these cosmic cataclysms. But the spacetime these waves travel through is not the perfectly smooth, idealized continuum of Einstein's equations. It is the quantum foam, a grainy, turbulent medium. As a gravitational wave passes through this frothy substrate, its journey is not perfectly pristine. The foam's chaotic structure would impart tiny, subtle distortions onto the wave, a kind of stochastic jitter. Imagine a perfectly smooth, clear signal traveling through a medium filled with countless infinitesimal lenses and prisms, each one slightly deflecting and scrambling the signal. Over an immense cosmic distance, these tiny, random interactions would accumulate, leaving a faint but statistically detectable signature of scatter in the gravitational wave signal. It would be like hearing a clear, pure note from a violin, but with a subtle, gritty texture superimposed upon it, the texture of spacetime's own grain. Future generations of gravitational wave observatories are being designed with this exact possibility in mind. Projects like the Laser Interferometer Space Antenna, or LISA, a planned space-based detector, will be exquisitely sensitive to low-frequency gravitational waves, the kind that have traveled across billions of light years. These ancient waves have spent eons propagating through the foam, giving the quantum noise the maximum possible time to leave its mark upon them. By analyzing the waveforms from many such events, astronomers could search for a consistent, non-random scrambling effect that cannot be explained by the sources themselves. Finding this signature would be a direct detection of the foam's structure. It would be the ultimate confirmation that empty space is not empty, but is a dynamic, vibrating entity, and it would provide our first ever empirical data about physics at the Planck scale, a realm forever beyond the direct reach of particle colliders. But the quest doesn't end with gravitational waves. Another tantalizing possibility involves the most ancient light in the universe, the cosmic microwave background radiation. This afterglow of the Big Bang has been traveling for nearly 14 billion years, and its polarization, the specific orientation of its light waves, carries a pristine record of the universe's infancy. The theory suggests that the quantum foam, if it possesses a particular kind of structure, could have imprinted a unique, swirling pattern on this polarization, known as a B-mode signal. While the primary source of such a signal is thought to be primordial gravitational waves from the inflation era, a component of it could very well be the fossilized impression of the spacetime foam, a snapshot of its texture from the universe's first moments. Disentangling this foam-induced signal from other sources is a monumental challenge, but it represents another potential channel through which the faint murmur of the quantum vacuum might finally be revealed. Detecting this cosmic noise would do more than just confirm a theory. It would fundamentally change our approach to fundamental physics. It would provide an observational anchor for theories of quantum gravity. Currently, ideas like loop quantum gravity, string theory, and causal dynamical triangulations make different predictions about the specific statistical properties of the foam. Is it foamy in all directions equally, or does it have a preferred spatial structure? Does it behave like a collection of random bubbles or a more organized polymer network? By carefully analyzing the specific way in which the foam distorts signals, we could, for the first time, perform experimental tests to distinguish between these competing models. The static would cease to be mere noise and would instead become a cosmic dial tone, connecting us directly to the underlying processor of reality, allowing us to audit the universe's most fundamental accounts. This transforms the quantum foam from a philosophical abstraction into a physical substance that can be probed, measured, and understood, opening a new chapter in humanity's quest to comprehend the very bedrock of existence. Now, if the quantum foam is a chaotic sea of flickering geometries and wormholes, its wild nature presents a monumental challenge for any theory hoping to unify gravity with quantum mechanics. But what if the problem isn't the foam itself, but the very way we picture the fundamental constituents of reality? This brings us to a theory that offers a radically different kind of ingredient, one that might just be able to smooth out the foam's roughest edges. Welcome to the elegant world of string theory and its profound relationship with the quantum foam. For decades, our most successful particle physics has treated electrons, quarks, and photons as zero-dimensional points, tiny, structureless dots. This picture works brilliantly until gravity enters the scene, and then the mathematics explodes into infinities when these point particles interact with the fluctuating spacetime of the quantum foam. It's like trying to calculate the precise physics of a pinhead on a trampoline that is itself jittering violently. The interactions become a mess of infinite energies that our equations cannot handle. String theory makes a breathtakingly simple yet profound shift in this paradigm. It proposes that the most fundamental entities in the universe are not point particles, but unimaginably small, one-dimensional vibrating strings. To grasp the scale, if an atom were enlarged to the size of our solar system, a string would be about as large as a single tree on Earth. These strings aren't made of anything smaller. They are the ultimate building blocks, and their different vibrational patterns are what manifest as the different particles we observe. One specific vibration gives you an electron, another a photon, another a quark, and so on. This shift from points to strings has a deeply calming effect on the tumultuous quantum foam. A point particle is a singularity. It exists at a single, infinitesimal location, and when it interacts with a frothing spacetime fluctuation, the forces involved can become infinite. But a string is an extended object. It has a finite, though minuscule, length. It doesn't interact at a single, sharp point. It smears its interactions out over its entire length. This smearing effect acts as a natural regulator, smoothing over the wildest, most infinite producing fluctuations in the foam. The vicious quantum jitter that causes calculations to blow up when point particles are involved becomes a manageable, finite ripple when interacting with the soft, extended structure of a string. It's the difference between balancing on the sharp point of a needle versus standing on a smooth, rounded hill. One is precarious and prone to disaster, while the other is stable and manageable. In the string theory picture, the foam is still there, but its sharpest, most destructive spikes are naturally blunted by the very nature of the strings vibrating within it. However, this elegant solution comes with a truly mind-expanding requirement, one that pushes the very boundaries of what we call reality. For the mathematical consistency of string theory to work, the universe cannot have only the three spatial dimensions and one time dimension we experience. The equations only settle down and produce a stable, finite theory in a spacetime of 10 or even 26 dimensions. This seems at first glance to be a fatal flaw. We clearly live in a world with three spatial dimensions: length, width, and height. So where are the others? The theory proposes that these extra dimensions are compactified or curled up into an infinitesimally small, complex shape at every single point in our familiar three-dimensional space. To visualize this, think of a long, thin garden hose. From a great distance, it looks like a one-dimensional line. But as you get closer, you realize it has a second dimension, a circular cross-section curled up so tightly that it was invisible from afar. In the same way, at every point in our three-dimensional world, there could be 6 or 7 extra spatial dimensions curled up into a fantastically intricate geometric shape called a Calabi-Yau manifold, far too small for us to perceive directly. This concept of hidden dimensions offers a spectacular new perspective on the quantum foam. The frantic, chaotic bubbling we've been discussing might not be limited to our 3 familiar dimensions. The true quantum foam is a higher dimensional phenomenon. What we perceive as a random, frothy fluctuation in our 3D space could be the shadow, the projection, of a much more complex and perhaps even orderly vibration occurring in the full 10-dimensional reality. The foam's apparent randomness might be an illusion born of our limited perception, like a 2-dimensional flatlander trying to make sense of a 3-dimensional object passing through its plane. In the full, higher dimensional space of string theory, the wild fluctuations of the foam could be tamed, organized into the harmonious vibrational patterns of the strings themselves. The unification of all forces, including gravity, then becomes a geometric necessity in this higher dimensional realm, with the distinct particles and forces we see merely being different facets of this underlying vibrational unity. Ultimately, string theory presents a universe where the bedrock of reality is not a chaotic, unpredictable froth, but a symphony. The quantum foam is the stage, but the strings are the musicians. Each fundamental particle is a different note played on these tiny, cosmic strings, and the laws of physics are the rules of harmony governing the symphony. The goal of this grand theoretical enterprise is to show that the apparent chaos of the quantum foam at the Planck scale is not a sign of fundamental lawlessness, but a complex piece of music we are only just beginning to learn how to read. It suggests that deep within the seething vacuum, at the very heart of reality, there exists an exquisite order and a profound connection between all things, woven together by the resonant vibrations of strings in a hidden, multi-dimensional cosmos. One of the most deeply felt experiences of our existence is the relentless, one-way flow of time. We remember the past, but we cannot remember the future. A shattered glass spontaneously reassembles itself in reverse only in science fiction. In our reality, entropy always increases and disorder grows. This is the arrow of time, a fundamental asymmetry woven into the fabric of our universe. But why should this be? The microscopic laws of physics, for the most part, are perfectly reversible. If you were to watch a film of 2 electrons colliding and scattering, you wouldn't be able to tell if the film was being played forward or backward. The event is symmetric in time. So, where does our overwhelming, macroscopic experience of a one-way temporal direction come from? A provocative theory suggests we must look to the very origin of the cosmos, to the state of the quantum foam in the first fleeting instance after the Big Bang, to find the source of time's irreversible arrow. The key to this idea lies in a concept from thermodynamics known as entropy. Entropy is a measure of disorder or the number of ways a system can be arranged. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. It's the reason your bedroom tends to get messier, not tidier, if you leave it alone. This ever-increasing entropy is what we perceive as the arrow of time. The puzzle has always been, why did the universe start in such an incredibly ordered, low-entropy state? Imagine a brand new deck of cards perfectly sorted by suit and value. This is a state of very low entropy. If you shuffle that deck, it becomes disordered. Its entropy increases, and you would never expect it to spontaneously shuffle itself back into perfect order. Our universe was like that pristine deck of cards at the moment of the Big Bang. It was in an exquisitely ordered, low-entropy state, and it has been shuffling itself into greater and greater disorder ever since. This initial condition is the ultimate source of why time has a direction for us. This is where the quantum foam enters the story with breathtaking force. In the first fraction of a second after the Big Bang, the universe was an unimaginably dense, hot, and energetic fireball. At these extreme energies, the very fabric of spacetime would have been dominated by the quantum foam in its most raw and active state. The entire cosmos was a seething, turbulent ocean of probability, with microscopic wormholes forming and collapsing, virtual particles bubbling up in a frenzy, and the geometry of space itself fluctuating wildly. This primordial foam was a state of maximum chaos at the microscopic level, but crucially, it was also a state of equilibrium. The incredible density and temperature meant that energy was distributed in a very particular, high-entropy way for that early, compact universe. It was a hot, dense, uniform soup, which represents a high-entropy state for a universe of that tiny size. Then, inflation struck. The universe underwent a period of hyper-fast expansion, blowing up from a subatomic speck to a volume larger than our entire observable cosmos in a virtual instant. As it expanded and cooled at a fantastic rate, it was suddenly ripped out of that initial foamy equilibrium. The rapid cooling effectively froze in place the particular configurations and asymmetries that were present in the quantum foam at that moment. Think of it like suddenly flash freezing a pot of boiling water. The bubbling, churning motion of the water molecules is the high entropy state. When you instantly freeze it, you capture a specific, random arrangement of bubbles and currents, locking them into the ice. That specific, frozen-in pattern is a snapshot of the chaos, but the ice crystal itself is a more ordered, lower entropy state compared to the raging boil. In the same way, the expansion of the universe froze the frenetic activity of the quantum foam, translating its microscopic, probabilistic chaos into the initial conditions for our macroscopic cosmos, conditions that were incredibly smooth and uniform on large scales, and therefore, paradoxically, in a state of very low gravitational entropy. This process set the stage for everything that followed. Because the universe started in this low entropy state, it had somewhere to go. The second law of thermodynamics kicked in, and the cosmos began its long, slow journey toward higher entropy. This drive is what powers the arrow of time. It is why galaxies form, why stars burn, why life evolves, and why we remember the past. The past is the state of lower entropy, and the future is the state of higher entropy. Our memories and records are themselves low-entropy structures that could only form as part of this grand, cosmic progression from order to disorder. The specific, frozen-in fluctuations from the primordial quantum foam are the reason the universe isn't perfectly smooth today. Those tiny density variations, stretched to cosmic proportions by inflation, became the gravitational seeds for galaxies, stars, and planets. So, the very structures that allow for the existence of complex beings like us, who can ponder the nature of time, are a direct consequence of the asymmetries locked in from the early quantum foam. This theory offers a profound and elegant connection between the very small and the very large, and between the beginning of time and our present experience of it. It suggests that the irreversible flow of time is not a fundamental law written separately into the cosmos, but an emergent property, a consequence of the unique initial conditions born from the quantum foam during the universe's birth. The reason we cannot remember the future is because the future is, by definition, a state of higher entropy, a state where the information needed to form a memory is more dispersed and disordered. The arrow of time is the universe's memory of its own incredibly ordered beginning, a memory that was imprinted into the fabric of reality when the seething frenzy of the primordial foam was suddenly quieted by the cosmic expansion, setting in motion the one-way journey from a past of exquisite order to a future of ever-increasing disorder that defines our reality and our very existence. Yet for all its profound theoretical implications, the quantum foam remains frustratingly beyond our direct gaze. Its scale is so unimaginably tiny, and its fluctuations so fleeting that we cannot simply build a powerful enough microscope to see it. So how do we move from elegant equations and philosophical speculation to hard, experimental fact? This challenge has pushed physicists to become cosmic detectives, devising extraordinarily ingenious and ambitious experiments to catch the faintest whisper of the foam's existence, turning the entire universe into a laboratory for probing the very foundations of reality. These are not your typical laboratory experiments. They are grand, long-distance observation campaigns that use the most distant celestial objects and the most precise machines ever built as our proxies for seeing the unseen. One of the most promising strategies involves staring deep into the cosmos, using the light from the most powerful and distant sources as a probe of the spacetime it travels through. The concept is beautifully simple in principle, though fiendishly difficult in practice. Imagine a fantastically bright quasar, a galaxy billions of light years away with a supermassive black hole at its heart, erupting in a brilliant flash of gamma rays. This flash contains photons of many different energies, from relatively low energy waves to tremendously high energy particles. In the perfectly smooth spacetime of classical physics, all these photons, despite their different energies, should travel at the exact same speed, the constant speed of light. They should all arrive at our telescopes in a perfectly synchronized pack after their multi-billion-year journey. But if spacetime is a churning quantum foam, this perfect synchronicity could be broken. The idea is that higher energy photons, with their shorter wavelengths, would interact more strongly with the fine-grained, lumpy structure of the foam. Think of it like trying to run through a forest. A large, slow-moving animal might not notice the small bushes and saplings, but a small, fast-moving one would be constantly dodging and weaving around every single tree trunk. In the same way, a high-energy gamma-ray photon might experience a tiny, cumulative drag or scattering effect as it navigates the microscopic bumps and wormholes of the foam, causing it to arrive a minuscule fraction of a second later than its lower-energy companions. Scientists using powerful instruments like the Fermi Gamma-Ray Space Telescope and the MAGIC telescope have been meticulously analyzing light from distant quasars and gamma-ray bursts, searching for exactly this kind of energy-dependent time delay. They look for a telltale lag, a spreading out of the light signal where the highest energy photons consistently arrive last. The expected time difference is almost laughably small, perhaps a few milliseconds over a journey of billions of years. Detecting such a subtle effect requires not only incredible timing precision, but also a deep understanding of the astrophysical sources themselves to rule out other causes for any observed delay. A confirmed detection would be a monumental breakthrough, a direct observational signature that the fabric of space itself has a texture, that the stage is not smooth, and that Einstein's perfect constant might be a macroscopic approximation of a much grittier underlying reality. Here on Earth, another front in this investigative war is being waged in the ultra-precise, climate-controlled silence of advanced physics laboratories. The weapon of choice here is the atomic clock, a device so astonishingly accurate that it would not gain or lose a second over the entire age of the universe. These clocks work by using the natural, incredibly stable vibration of atoms, like cesium or strontium, as a pendulum. The theory is that the quantum foam's chaotic fluctuations would introduce a fundamental limit to this stability. The constant jitter of spacetime at the Planck scale would create a subtle, intrinsic noise floor, a faint fuzziness that would prevent any clock, no matter how perfect, from measuring time with infinite precision. It would be like trying to mark time with a stopwatch in the middle of a bubbling, frothing liquid. The very mechanism you're using to measure is itself being jostled by the medium. Researchers are now comparing the ticks of the world's best atomic clocks, looking for tiny, random desynchronizations between them. If two perfectly engineered clocks, isolated from all other known sources of vibration and electromagnetic interference, slowly drift out of sync in a particular, random way, it could be the signature of the quantum foam's background noise shaking their atomic pendulums. Other laboratory experiments involve fantastically precise laser interferometers, similar to those used to detect gravitational waves but pushed to even greater sensitivities. These devices measure the distance between mirrors with a precision smaller than the diameter of a proton. The concept is that the quantum foam would cause the very geometry of space between the mirrors to fluctuate. The distance between them would not be a fixed static number but would exhibit a fundamental, irreducible jitter. Detecting this so-called holographic noise would be like seeing the individual pixels on the cosmic projector screen, proving that spacetime is fundamentally pixelated and that the smooth continuum we experience is an emergent illusion. The technological challenges involved in these experiments are almost as mind-bending as the theories they seek to test. They operate at the very boundaries of what is possible, requiring heroic efforts to shield the experiments from the cacophony of everyday reality, from seismic rumbles and temperature changes to the magnetic hum of modern civilization. Isolating a signal that may be born from the Planck scale is like trying to hear a single, specific snowflake land in the middle of a roaring hurricane. It requires not just precision, but a profound understanding of every possible source of noise so that whatever signal remains can be attributed with confidence to the quantum foam itself. What would it mean if one of these experiments finally succeeded? A positive detection would arguably be one of the most significant discoveries in the entire history of science. It would provide the first direct experimental evidence for a theory of quantum gravity, validating decades of theoretical work and immediately ruling out whole classes of models that fail to predict the observed effect. It would confirm that space and time are not fundamental, but emergent properties of a deeper, discrete reality. We would have to rewrite our textbooks, fundamentally altering our understanding of the universe from its very foundations. More than that, it would open up an entirely new field of experimental physics, quantum gravity phenomenology. We would no longer be theorizing in the dark, we would have data. We could begin to characterize the foam's properties. Is it isotropic, the same in all directions, or does it have a preferred structure? Is it like a random foam of bubbles or a more organized spin network? The faint static we detect would become a cosmic Rosetta Stone, allowing us to finally decipher the language in which the deepest laws of the universe are written. This is the ultimate experimental frontier, a quest to touch the fabric of reality itself, and its success would mark the beginning of a new era in human understanding. After exploring the cutting-edge experiments striving to detect the quantum foam, we arrive at a point where physics and philosophy converge, compelling us to step back and ask what this churning foundation of reality truly means for our understanding of existence itself. This isn't just about equations and particles, it's about the very nature of being, causality, and whether the universe we perceive is ultimately built on a bedrock of rigid determinism or pure, unfettered chance. The quantum foam forces this profound confrontation, challenging the classical, intuitive picture of a stable, reliable cosmos and replacing it with a vision that is fundamentally fluid, probabilistic, and startlingly alive. Consider the classical worldview that dominated for centuries, from Newton to Einstein. In this perspective, the universe is a vast, predictable clockwork. If you knew the precise position and momentum of every single particle, you could, in principle, calculate the entire future and rewind the entire past. Reality was considered deterministic, a chain of cause and effect so unbreakable that every event was seen as the inevitable consequence of what came before. This provided a comforting sense of order, a cosmos governed by immutable laws on a smooth, continuous stage. The quantum foam shatters this comforting image entirely. At the Planck scale, that stage itself is revealed to be a seething maelstrom of spontaneous activity. Virtual particles pop into existence from what seems like nothing, borrowing energy from the universe in a direct defiance of classical conservation laws, only to vanish again. Microscopic wormholes flicker in and out of being, creating and destroying potential connections across spacetime. This isn't minor static, it is a foundational chaos, a realm where the very concepts of something and nothing lose their distinct meaning. The foam suggests that at its heart, reality is not determined, but is a continuous creative process of becoming, where possibility is more fundamental than actuality. This inherent randomness at the base of reality forces a radical rethinking of the principle of causality, the idea that every effect must have a preceding cause. In our smooth, large-scale world, this principle holds firm. A baseball breaks a window because it was thrown, but in the quantum foam, this linear chain becomes blurred. With microscopic wormholes potentially creating shortcuts in spacetime and wild geometry fluctuations, making the sequence of events probabilistic, the very notion of before and after can become fuzzy at the most fundamental level. While the chronology protection conjecture likely prevents macroscopic paradoxes, the foam implies that at the ultra-small scale, causality might not be an iron law, but rather a strong statistical tendency that emerges from the averaging of trillions of these acausal fluctuations. The universe, it seems, operates with a degree of spontaneity at its core, where events can simply happen without a clear, deterministic cause, born directly from the fertile ground of quantum potential. This doesn't make our macroscopic world unpredictable, but it does mean that the bedrock upon which it sits is not one of clockwork certainty, but of dynamic, creative uncertainty. These physical revelations plunge us directly into deep philosophical waters, most notably the ancient debate between realism and anti-realism. Realism, in its simplest form, is the belief that a physical world exists independently of our observation of it. The moon is there whether anyone is looking at it or not. Quantum mechanics and the foam by extension has always posed a challenge to this view. The transactional interpretation, for instance, with its waves from the future, or the role of the foam in dynamical collapse models, suggests that the act of observation or interaction is not a passive reading of a pre-existing state, but an active participant in bringing that state into being. The foam can be seen as a physical manifestation of this. It is not that a definite particle is jostled by a definite foam. Rather, the particle's very existence as a localized entity might be a consequence of its continuous interaction with the frothy vacuum. The world is not a collection of definite objects, but a web of potentialities, and what we call reality is the stable pattern that crystallizes from this web through immense numbers of these quantum interactions. The solidity of the world is then a compelling and persistent illusion, a consensus reality that emerges from an underlying realm of pure potential and relation. Ultimately, the quantum foam invites us to adopt a more fluid and humble perspective on our place in the cosmos. It displaces us from a universe centered on human certainty and reveals one that is fundamentally participatory and creative. The laws of physics are not like the rigid rules of a board game decreed from on high. They are more like the habits of a complex system, stable patterns that have emerged over billions of years from the dynamic, self-organizing chaos of the Planck scale. This view doesn't diminish the wonder of the cosmos, it amplifies it. We are not mere spectators in a predetermined drama. We are active, physical processes within this unfolding reality, our own consciousness and observations woven from the same vibrating, probabilistic stuff as the galaxies and the vacuum itself. The quantum foam teaches us that the universe is not a frozen, static sculpture, but a living, breathing, and continuously creative process, and our ability to ponder its mysteries is perhaps the most beautiful and intimate expression of that ongoing creation. After a journey across 30 mind-expanding theories, from pixelated spacetime lattices to emergent holographic realities, we arrive at our final destination, not with a conclusion, but with a launch pad into the future. The study of the quantum foam is far from over. In many ways, it is just beginning. As we stand on the precipice of a new era in physics, two powerful currents are converging. the refinement of breathtaking theoretical frameworks, and the dawn of technologies that may finally let us touch the fabric of spacetime itself. One of the most promising theoretical paths forward is the idea of asymptotic safety in quantum gravity. For decades, the primary challenge has been that when we try to apply quantum rules to gravity, the math explodes into uncontrollable infinities. Asymptotic safety offers a brilliant escape route. Imagine a mountain with a treacherous, infinitely high peak representing those infinities. Most attempts to climb it fail. But asymptotic safety suggests there's a gentle, safe path to the summit, a special trajectory where the strength of gravity changes with the energy scale in just the right way so that all the infinities cancel each other out. At very high energies, near the Planck scale where the quantum foam reigns, gravity would become safe, its behavior predictable and finite. This isn't just a mathematical trick. It would mean that quantum gravity is a perfectly well-behaved theory in its own right, one that we could use to make solid predictions about the foam's structure without the equations breaking down. It provides a compelling vision of a universe where the apparent chaos of the foam is governed by a deep, hidden order, a cosmic balance that keeps the foundational layer of reality stable and coherent. To test such profound ideas, we need to move beyond indirect observations and build machines that can directly probe the Planck scale. While that might seem forever out of reach, since building a collider powerful enough would need to be the size of a galaxy, scientists are devising incredibly clever workarounds. The next generation of gravitational wave observatories, like the Laser Interferometer Space Antenna, or LISA, will open a completely new window. By measuring the ripples in spacetime from the mergers of supermassive black holes, LISA will listen for the subtle scattering of gravitational waves after they have traveled billions of light years through the quantum foam. The accumulated jitter on these ancient waves could carry the unique statistical fingerprint of the foam's texture, telling us if it's more like a random bubble bath or an orderly spin network. Even further ahead, plans are being drawn for experiments that will use the entire Earth as a gravitational wave detector by precisely monitoring the distances between satellites in orbit, creating a web of measurement so sensitive it could detect the faint holographic noise of spacetime's pixelation. But the future extends beyond simply observing from afar. It may involve manipulating the vacuum itself. The field of quantum optics is advancing at a staggering pace, with scientists learning to sculpt the quantum vacuum with ultra-intense lasers. By creating cavities and structures that alter the allowed modes of virtual particles, we might one day be able to feel the foam's structure indirectly, perhaps by measuring minute forces or shifts in energy levels that betray the presence of underlying spacetime grain. Another frontier lies in ultra-cold quantum gases. By cooling atoms to a fraction of a degree above absolute zero, we can create Bose-Einstein condensates, a state of matter where thousands of atoms behave as a single quantum wave. These laboratory-scale universes can be used to simulate the hypothesized behavior of spacetime itself, allowing us to watch how a synthetic quantum foam might form and evolve under controlled conditions, providing tangible analogies for processes we could never witness directly in the cosmos. Each of these approaches is like developing a new sense, a new way of perceiving a reality that has been hidden from us since the dawn of time. Ultimately, the greatest discovery in the future of foam research may not be a single observation or a confirmed theory, but a fundamental shift in our understanding of reality's language. For centuries, we have described the universe in terms of particles and forces existing in space and time. The quantum foam suggests that the next great synthesis will describe everything particles, forces, space, and time as excitations or patterns of a single underlying substance. The frantic foam is not a secondary phenomenon, it is the primary reality. Our journey to comprehend it is more than a technical challenge. It is a voyage to the source of existence, a quest to read the original code of the cosmos. The theories we have explored today are not 30 different answers, but 30 different paths up the same magnificent mountain. As new experiments come online and new theoretical insights emerge, we are not closing the book on the quantum foam. We are turning the page to a new chapter, one that promises to reveal a universe even more mysterious, more interconnected, and more wonderfully strange than we have yet dared to imagine. The foam is the frontier, and the exploration has only just begun. And so, our incredible journey through the quantum foam comes to a close, a voyage that has taken us from the very edge of human comprehension to the turbulent foundation of reality itself. We've explored a universe that is not the silent, empty void of classical imagination, but a seething, dynamic ocean of pure potential. We began by reimagining the fabric of space and time, discovering it might be pixelated into a spacetime lattice, a fundamental grid that sets the ultimate resolution for the cosmos. We then dove into the chaotic dance of virtual particle pairs, a ceaseless creation and annihilation that provides the very pressure of empty space and even powers the slow evaporation of black holes through Hawking radiation. We navigated the labyrinthine wormhole nexus, a vision of a deeply interconnected cosmos where every point is linked by microscopic bridges, and then stepped into the holographic principle, where our rich three-dimensional reality might be nothing more than a magnificent illusion projected from a two-dimensional surface at the edge of everything. The journey grew even more profound as we encountered the woven loops of spin networks in loop quantum gravity, a tapestry of space that eliminates the terrifying infinities of singularities and suggests our universe may have been born from a great bounce rather than a single Big Bang. We saw how causal dynamical triangulations builds reality from the ground up with simple geometric blocks, and then confronted the chilling evaporation of time itself in the quantum realm, where the familiar river of time shatters into a multitude of probabilistic local clocks. We grappled with the possibility that the foam's relentless energy is the very engine of cosmic acceleration, dark energy itself, and faced the staggering numerical catastrophe of the cosmological constant problem, a discrepancy so vast it highlights a fundamental flaw in our current understanding. We witnessed the foam's destructive power at the event horizon of black holes and dared to consider that even Einstein's constant speed of light might falter in the froth, a potential crack in the bedrock of relativity. We explored theories that the universe actively protects its own timeline through the chronology protection conjecture, and then expanded our vision to a multiverse, an infinite cosmic foam where our entire cosmos is just one bubble in an eternally inflating meta-universe. We saw the foam as the potential origin of cosmic inflation, the sculptor of the universe's large-scale structure, and even as the medium for a transactional handshake across time that defines reality. We delved into theories where the foam itself solves the measurement problem, providing the constant noise that collapses quantum possibilities into classical certainty, and entered the fuzzy, uncertain world of non-commutative geometry, where the very concept of a precise location dissolves. We uncovered the deep link between the foam and black hole thermodynamics, revealing the event horizon as the most complex information storage system in existence, and pondered the radical idea that space-time could be a superfluid, with particles and forces emerging as defects and excitations in its flow. The exploration continued through the mind-bending emergent spacetime paradigm, where space, time, and gravity are not fundamental, but are collective illusions arising from a vast network of quantum entanglement, a universe that is, at its heart, a cosmic computation. We tested the limits of Einstein's relativity with the search for Lorentz violation, and built reality from knots of light itself with Wheeler's visionary gens. We confronted the hierarchy problem, the perplexing weakness of gravity, and the potential solutions offered by supersymmetry and hidden extra dimensions. We saw how the foam's gravitational jitter could be the key to gravitational decoherence, and we learned how scientists are now hunting for the faint cosmic noise of the foam in gravitational waves and the light from distant quasars. We soothed the foam's infinities with the elegant vibrations of strings in hidden dimensions, and finally, we traced the one-way arrow of time itself back to the unique, low-entropy state frozen into the universe from the primordial quantum foam. This, then, is the final frontier of physics, not in the distant stars, but in the unimaginably small, turbulent space between and within everything. The quantum foam is more than a theory. It is the central mystery, the place where our most successful theories meet and break down, forcing a revolution in our understanding. It challenges our notions of reality, causality, and time, suggesting a cosmos that is fundamentally alive, creative, and participatory. Our voyage through these 30 theories reveals a universe far stranger, more interconnected, and more wondrous than we ever dreamed. Now the conversation turns to you. With so many mind-expanding ideas to choose from, which one of these theories completely reshaped your view of reality? Was it the holographic universe, the emergent spacetime, or the cosmic interconnectedness of the wormhole nexus? Let us know in the comments below which concept blew your mind the most. And if you're ready to continue exploring the deepest mysteries of the cosmos, make sure to subscribe and hit the notification bell so you don't miss our next deep dive into the wonders of the universe. The journey into the unknown